Imagine pouring concrete for a factory floor without checking the dimensions first. Once it cures, moving a wall is a nightmare that costs time and money. In Azure, your virtual network address space is exactly that hardened concrete. You must plan CIDR ranges like 10.0.0.0.16 and subnets before deployment, because changing addresses later forces you to delete virtual machines and application gateways, triggering unavoidable downtime and breaking dependent service connections. We will cover CIDR math and reserved IPs, the critical gateway subnet rule, hub-and-spoke topology for enterprise scale, and common pitfalls to avoid on the exam. You will learn to calculate usable IP counts using standard 24 blocks, configure named subnets for ExpressRoute gateways, and apply peer links between virtual networks. Mastering these concepts directly impacts your AZ-305 score and prevents costly network redesigns in production environments where traffic routing fails. Start with CIDR notation. A 16 gives you 65,536 addresses, while a 24 provides exactly 256 total IPs. Azure automatically reserves 5 specific addresses in every subnet for the network identifier, default gateway, 3 service placeholders, and broadcast traffic. You lose these to overhead, so always calculate usable capacity based on your maximum instance count plus a safety buffer to prevent deployment failures during scale-up events. The gateway subnet is a mandatory requirement for VPN and ExpressRoute gateways. Azure strictly requires the subnet name to be exactly gateway subnet with that precise casing. This dedicated space cannot host virtual machines or load balancers, so you should size it as a 27 or 28 prefix to accommodate gateway scaling operations. Failing to follow this naming convention will immediately trigger provisioning errors and block all site-to-site connectivity tests. First, plan your CIDR ranges and tier subnets to separate web, app, and database traffic logically. You should assign distinct 24 blocks like 10.1.1.0.24 for front-end tiers and 10.1.2.0.24 for backend databases within the same virtual network. This logical separation allows you to attach specific network security groups later, preventing unauthorized lateral movement and ensuring compliance during routine audit reviews. This Terraform block defines a production virtual network with a 16 address space in East US. We then create subnets for the web and database tiers, assigning specific 24 prefixes to segment traffic and apply network security groups later. You will use the Azure subnet resource to enforce these boundaries, which directly prevents cross-tier communication leaks and simplifies troubleshooting during performance degradation incidents. Next, reserve the gateway subnet with a 27 or 28 prefix to ensure the VPN gateway has enough IP space for scaling and high availability. You must allocate at least 32 addresses to support multiple virtual network gateway instances across availability zones. Skipping this step will force you to delete the entire gateway configuration later, causing extended connectivity outages for all connected branch offices. Here we define the gateway subnet in Bicep using a standard resource block. Notice the name property must be exactly gateway subnet with no variations. We assign a 27 prefix to provide 32 addresses, ensuring the gateway has room for scaling without consuming too much of your address space. This precise configuration prevents provisioning failures and keeps your overall network design compliant with enterprise security standards. Finally, validate that your cloud CIDR does not overlap with on-premises ranges and leave gaps for future growth to avoid refactoring pain. You should audit your 10.0.0.0.16 backbone against local server blocks like 192.168.0.0.24 before establishing site-to-site connections. Overlapping address ranges will break routing tables entirely, forcing emergency network migrations that disrupt business operations and trigger compliance violations during peak transaction hours. This CLI command creates a subnet with service endpoints for Azure SQL using the AZ network VNet subnet create syntax. Using endpoints routes traffic over the Microsoft backbone instead of the public internet, improving security and performance while keeping your address space clean. You will configure private link services to restrict database access strictly to authorized subnets, which eliminates external exposure and satisfies strict regulatory audit requirements. Compare these approaches carefully before finalizing your design. Using a for a web tier risks IP exhaustion quickly when auto-scaling groups spin up additional virtual machines. Ignoring growth gaps leads to refactoring downtime that halts production deployments. Hub and Spoke centralizes management and improves security scalability by routing all intervirtual network traffic through centralized firewall appliances, which simplifies monitoring and enforces consistent policy enforcement across the entire environment. In Hub and Spoke topology, spokes contain application workloads and peer directly to the hub virtual network. The hub hosts shared services like firewalls and DNS resolvers for all connected branches. This design centralizes management and reduces complexity compared to mesh peering by consolidating traffic inspection at a single control plane. You will configure virtual network peering links with specific routing options to ensure seamless cross-environment communication without exposing internal endpoints publicly. Test your CIDR knowledge with a practical calculation scenario. A 24 subnet provides 256 total addresses across the entire block. With 5 reserved IPs automatically deducted by the platform, how many usable IPs remain for resources? You must subtract those overhead addresses to determine exact capacity limits, which directly prevents deployment failures when provisioning large-scale virtual machine scale sets during peak workload periods. Plan early, change late is expensive when dealing with core infrastructure components. A well-planned address space prevents costly refactoring and downtime later by establishing clear boundaries before any resources are deployed. You will save hundreds of engineering hours by documenting CIDR allocations up front, which eliminates emergency network rewrites and ensures your architecture remains stable during routine maintenance windows and major platform upgrades. We covered CIDR math and reserved IPs, the gateway subnet rule, hub and spoke topology, and common pitfalls encountered during certification exams. Remember to plan subnets carefully, reserve gateways with exact naming conventions, and validate overlap before publishing your architecture diagrams. Mastering these foundational steps will directly improve your exam score while simultaneously preventing production network failures that disrupt critical application delivery pipelines. For AZ-305, focus heavily on gateway subnet naming and sizing requirements during the networking module. Know CIDR math cold and practice calculating usable IP counts for 24 blocks under timed conditions. Hub and Spoke is strongly preferred for multi-app environments, so avoid selecting subnets for large tiers in exam scenarios. Use infrastructure as code templates to document topology accurately and demonstrate practical architectural competence. Picture a high-security research facility with distinct zones like a public lobby, a secure lab, and an armored vault. You would never leave the doors between these areas wide open, or sensitive data would be exposed to anyone walking by. Cloud networking works exactly the same way. Subnetting divides your IP space into isolated zones, while segmentation enforces strict rules using Azure Network Security Groups to control traffic between them. Mastering this design prevents lateral movement and keeps your architecture manageable as it scales. Today, we will break down exactly how to design a resilient network structure. We start with the mechanics of CIDR notation and subnet masks, then move into building a secure three-tier architecture using Azure Virtual Networks. Next, we examine segmentation strategies like NSGs and NACLs, focusing on port 5432 for database isolation. Finally, we cover the best practices you need to apply for production-scale deployments, ensuring you avoid misconfigured routing tables that could accidentally expose sensitive workloads to the public internet. Every IP address relies on a subnet mask to tell devices which bits belong to the network and which identify individual hosts. CIDR notation simplifies this by using slash notation, like a 24, to represent the number of fixed network bits. This mathematical approach lets you calculate exactly how many usable addresses each segment provides, ensuring you allocate just enough space for your current workload while leaving room for growth without wasting address space. Misallocating a large range will quickly exhaust IPs and trigger deployment failures in Azure. While subnetting handles the logical division of your IP space, network segmentation is the active enforcement layer. It uses firewalls, routing tables, and access control lists to dictate exactly how data moves between those isolated zones. Understanding this distinction is critical because you can have perfectly sized subnets that still fail security audits if the segmentation policies are too permissive. You must explicitly configure NSG rules to block port 3389 for administrative access. Otherwise, attackers will easily pivot through exposed management endpoints. A secure cloud deployment typically follows a three-tier model to enforce strict boundaries. The public tier handles internet-facing assets and load balancers, using a 24 range to accommodate scaling fronts. The application tier routes internal business logic through a dedicated subnet, isolating compute from the edge. Finally, the data tier houses sensitive storage and database engines, ensuring that your most critical assets remain completely separate from external traffic paths. Failing to isolate these tiers allows cross-tier attacks that compromise entire environments during certification audits. First, we allocate non-overlapping CIDR blocks to establish the foundational address space for your environment. This initial step ensures that every subnet has a unique range, preventing routing conflicts before you even deploy resources. You should assign distinct ranges like 10.0.10.24 and 10.0.20.24 during planning. Skipping this validation causes overlapping address errors that halt VM provisioning and force expensive redeployment cycles in production Azure subscriptions. This Terraform configuration establishes the core virtual network with a broad 16 range, then explicitly defines two distinct subnets. The public subnet receives a 24 block for internet-facing workloads, while the data subnet gets its own isolated 24 range. Each resource declares its specific CIDR block and applies descriptive tags to track ownership across your infrastructure code. Applying this pattern prevents IP exhaustion and ensures compliance with least privilege network policies during certification exams. Next, we map each architectural tier to its dedicated subnet and enforce strict isolation boundaries. This step translates your logical design into concrete network segments that prevent unintended communication paths between different workload types. You must configure explicit route tables to direct traffic through Azure Firewall or NAT gateways. Neglecting this routing configuration creates open mesh networks where compromised virtual machines can freely scan and attack adjacent database clusters. This JSON configuration defines a security group rule that explicitly allows Postgres traffic on port 5432. Notice how the source address prefix restricts access to only the application tier subnet, ensuring that database ports remain closed to all other network segments. The priority field determines evaluation order, allowing you to layer multiple rules cleanly without conflicts. Setting priorities below 500 automatically overrides broader allow rules, which could accidentally expose sensitive storage endpoints to unauthorized clients. Finally, we enforce least privilege policies directly through infrastructure as code to maintain consistent security boundaries. Automating these rules eliminates manual configuration drift and ensures that every subnet adheres to your organization's compliance standards from the moment it deploys. You should implement automated policy checks using Azure policy definitions that reject non-compliant network configurations. Bypassing these safeguards allows unauthorized egress traffic that violates audit requirements and triggers immediate security incidents. This bicep snippet creates a network security group that explicitly denies all outbound traffic by default. The deny rule sits at priority 4096, acting as a safety net that blocks any unapproved egress connections. By defining this in code, you guarantee that databases cannot initiate random outbound calls, keeping your segmentation policies strictly enforced across every deployment. You must also configure explicit allow rules for Azure SQL endpoints to prevent legitimate application queries from failing during runtime. Beyond standard security groups, you will encounter network access control lists that operate at the subnet level. Unlike stateful firewalls, NACLs evaluate rules independently for ingress and egress, making them ideal for blocking specific malicious IP ranges or applying coarse-grained filters. In modern containerized environments, microsegmentation takes this further by enforcing policies directly on individual pods, ensuring security follows the workload regardless of its underlying network location. Failing to sequence NICL rules correctly causes legitimate traffic drops that disrupt critical production workloads. This principle should guide every segmentation decision you make. When a web server does not need direct database access, your network policy must explicitly block that path. Designing for minimal communication reduces your attack surface significantly and ensures that any compromised resource cannot easily pivot across your infrastructure. You must verify rule priorities using the AS Network NSG rule list command to confirm that restrictive deny statements override broader, allow rules during certification scenarios. Let's test your knowledge on applying these concepts. Consider a scenario where you need to prevent a compromised web server from directly accessing your database. The most effective approach involves implementing strict security group rules that only permit traffic from the designated application tier, while explicitly blocking all direct public access to the data subnet. You must also configure explicit deny rules for port 5432 to prevent lateral movement during active penetration testing exercises. Visualize how traffic moves through your segmented architecture. An external client request hits the public load balancer, which forwards authenticated traffic to the application tier. The application servers then process the logic and securely query the data storage tier. Each hop crosses a security boundary that validates permissions before allowing data to pass forward. You must configure private endpoints instead of public IP addresses to ensure database queries never traverse the public internet backbone. We covered the essential mechanics of subnet design and segmentation. CIDR notation establishes your address boundaries, while tiered architecture logically isolates workloads across public, application, and data zones. Segmentation policies enforce strict traffic rules to prevent unauthorized access, and automation ensures these configurations remain consistent over time. Mastering these concepts builds a resilient foundation for cloud infrastructure by preventing misconfigured NSG rules from exposing critical production databases during certification exams. For the AZ-305 exam, focus on memorizing standard CIDR ranges for each architectural tier and clearly distinguishing between stateful security groups and stateless NACLs. You will likely encounter scenarios requiring you to apply least privilege principles to network rules, so practice identifying overly permissive configurations. Always choose infrastructure as code solutions that guarantee consistent segmentation across your deployed environments. Reviewing official Microsoft documentation on virtual network peering limits will prevent costly architectural mistakes during performance testing. Picture a major railway junction where every branch line converges on a central station. If you want to travel from one branch to another, you must pass through the hub. There are no direct tracks between the branches. This is exactly how the hub-spoke topology structures cloud networking. In Azure, all traffic flows through a central virtual network that enforces security and manages connectivity. You will use this pattern with Azure Firewall and route tables to keep workloads isolated. If you skip this design, lateral movement attacks can spread instantly across your environment. In this lesson, we will explore the hub-spoke architecture thoroughly. We will define the distinct roles of the central hub and isolated spokes, examine how transit routing actually works in Azure, and walk through a complete Terraform implementation for virtual network peering. You will also review critical best practices to avoid common pitfalls on the certification exam. Understanding these configurations directly impacts your ability to design secure multi-tenant environments without exposing development data to production networks. The hub-spoke model is built on a strict hierarchy that simplifies enterprise networking. The hub acts as the central connectivity point, typically hosting shared Azure Firewall instances, VPN gateways, and centralized logging servers. Spokes are individual virtual networks dedicated to specific workloads or departments. They connect exclusively to the hub, but never communicate directly with each other. This design drastically reduces configuration complexity by centralizing management and eliminating the messy mesh of peering connections that usually breaks down in large organizations. A critical concept in this topology is transit routing, which fundamentally changes how traffic moves between networks. In cloud environments, you must explicitly enable gateway transit on the hub virtual network. This specific setting allows connected spokes to securely use the central VPN or ExpressRoute gateway for outbound internet traffic. Without enabling this flag, every single spoke would require its own dedicated gateway instance, dramatically increasing monthly costs and creating a massive management overhead that exam scenarios frequently penalize. Let's implement this topology directly using Terraform to automate your infrastructure provisioning. We will start by defining the core virtual networks that form the absolute foundation of your architecture. You must carefully assign non-overlapping CIDR blocks to prevent routing conflicts later in the deployment pipeline. Getting these address spaces correct from the beginning saves hours of debugging and ensures your peering links establish successfully without triggering validation errors during the apply phase. Here we define the hub and spoke virtual networks using standard Azure networking resources. Notice the address spaces are strictly distinct, assigning 10.0.0.0.16 for the central hub and 10.1.0.0.16 for the development spoke. Overlapping ranges would completely break routing tables and cause immediate connectivity failures across your environment. Both resources reside in the same region and resource group to simplify lifecycle management and prevent cross-region latency issues that frequently appear on certification scenarios. Next, we establish the bidirectional peering links that connect your isolated networks together. You must create the peering resource in both directions because Azure does not automatically propagate routes across a single link. This explicit two-way configuration ensures traffic flows reliably between the hub and spoke without requiring manual route table updates on every subnet. Failing to configure both directions will immediately break internetwork communication and cause routing timeouts during your deployment validation. This code block creates the actual peering resources with precise configuration flags. We explicitly set allow forwarded traffic to true so the central hub firewall can inspect traffic passing through before routing decisions occur. Crucially, we enable gateway transit on the primary link, allowing the spoke to securely use the hub's ExpressRoute gateway for outbound connectivity. Missing these flags will force direct internet egress and completely bypass your security inspection controls during runtime. Understanding the division of labor between these networks is absolutely key for certification success. The central hub hosts shared infrastructure like Azure Firewall instances, DNS forwarders, and monitoring agents. Spokes hold only the actual application workloads and databases. Peering simply allows connectivity, but the hub remains the strict control plane for security policies and routing decisions. Confusing these roles will cause you to misplace critical resources and fail practical design questions on the exam. Visualize the actual data flow as it moves through your configured networks. Traffic originates inside a spoke subnet, routes directly to the hub via peering, and passes through the next-generation firewall for deep packet inspection. The traffic then exits securely to the public internet or reaches another destination network. This deliberate choke point ensures every single packet is monitored and logged. Bypassing this path leaves your environment completely exposed to unfiltered threats and compliance violations. Remember this fundamental principle when making architectural design decisions for your certification exam. Centralize control and security policies strictly in the central hub, but keep that network absolutely lean. Do not place heavy application logic or compute workloads there under any circumstances. The hub exists solely for networking, routing, and management functions. Overloading it will degrade performance metrics and trigger architectural failure scenarios that frequently appear on practical assessments. Test your understanding with this practical scenario before moving forward. If a developer in the development spoke needs to access a database in the production spoke, exactly how does that traffic flow through your infrastructure? The correct answer reveals a common exam trap regarding direct peering restrictions and routing table configurations. You must route that request through the central hub firewall first. Otherwise, you will accidentally create an unauthorized direct pathway that violates security boundaries. Best practices include strict IP address management to avoid overlapping subnets, and reserving the central hub for shared services like ID domain controllers or DNS forwarders. A major pitfall is ignoring user-defined routes entirely, because simply peering networks does not automatically direct traffic. You must explicitly configure UDRs in spoke subnet configurations to point internet egress directly to the hub firewall IP address. Skipping this step breaks your security model and causes immediate compliance failures during audits. We covered the complete hub-spoke topology, defined transit routing and gateway transit flags, implemented peering configurations with Terraform, and reviewed critical best practices for exam success. The central hub strictly manages security policies and routing decisions, while spokes remain completely isolated workloads connected only through that central point. Mastering this separation ensures you can design scalable architectures that pass real-world security audits and consistently score high on practical certification assessments. For the AZ-305 exam, focus heavily on gateway transit settings within peering configurations and the absolute necessity of UDRs for proper routing. You will likely be asked to identify security gaps where spoke traffic bypasses the central hub firewall due to missing route tables or misconfigured subnet associations. Practicing these specific configuration checks will prevent you from falling into common distractor traps and ensure you select the most secure architectural design during timed practical questions. Imagine a global logistics company coordinating shipments between New York and Tokyo. If every warehouse built its own direct road to every other location, the map becomes a tangled mess of expensive routes. Now picture a central airport system where cargo flows through optimized hubs on a single managed network. That is exactly what Azure Virtual WAN does for enterprise connectivity. It replaces chaotic meshes with unified global fabrics, saving thousands in peering costs and preventing routing loops during peak traffic spikes. In this lesson, we will explore the global transit concept that powers Virtual WAN. We will examine core components like regional hubs and routing intent policies. Then we will walk through designing a secured hub with Azure Firewall Standard SKU. Finally, we will cover implementation details to avoid common pitfalls on your AZ-305 exam, where you must quickly identify when to use managed transit versus manual peering for compliance workloads. Azure Virtual WAN is built on a global transit architecture that simplifies connecting branch offices, remote users, and VNets by providing a managed network fabric. Instead of managing individual peering connections for every network pair, you connect everything to the Virtual WAN service. This reduces operational overhead significantly, allowing you to cut gateway counts by up to 80% while preventing misconfigured route propagation across multiple regions. Let us define the Virtual WAN Hub as a Microsoft-managed virtual network that acts as the central point of connectivity within your instance. This is where you deploy gateways like S2S VPN or Azure Firewall. You cannot modify the route tables directly through the portal interface. Instead, you must use routing intent to control traffic flow, which prevents accidental subnets from breaking production workloads. How does Virtual WAN compare to traditional networking? In a traditional hub-and-spoke model, you manage every peering connection manually, and routing tables become complex as you add branches. With Virtual WAN, the fabric automates routing intent and scales automatically across 50 regions. You get predictable performance over the Microsoft backbone, whereas traditional models rely on public internet routes that introduce jitter and fail compliance audits. Here is how data flows in a Virtual WAN design. Branch offices connect to the nearest hub via site-to-site VPN or SD-WAN appliances. Remote users connect via point-to-site VPN using native client software. VNets are peered into the hub using standard virtual network links. Traffic between branches traverses the Microsoft backbone through the hubs, bypassing the public internet entirely and ensuring secure routing across your infrastructure. Let us design a secured hub step by step to ensure your architecture meets enterprise standards. First, we define the Virtual WAN container using the AZ-network VWAN command to establish the global fabric. This sets the stage for all connectivity and prevents orphaned resources from accumulating in your subscription, which quickly becomes a governance nightmare during security audits and cost optimization reviews. Here is the Terraform code to create the Virtual WAN container. We define the resource with a name and specify the location like East US. This creates the top-level VWAN instance that will hold our hubs and gateways. You must assign a unique SKU tier, otherwise the platform defaults to basic features that lack advanced routing capabilities required for multi-region compliance deployments. Next, we provision a secured hub with Azure Firewall Standard. This integrates security inspection directly into the hub architecture. The firewall becomes the mandatory next hop for traffic destined for the internet or other VNets. If you skip this step, unfiltered traffic will leak through default routes, exposing sensitive databases to brute force attacks and violating strict regulatory frameworks like HIPAA. This Terraform snippet creates a secured hub by linking the hub to the VWAN and specifying an address prefix like 10.0.0/24. The firewall block integrates Azure Firewall directly, enabling security inspection for all transit traffic. You must configure threat intelligence mode as alert or deny. Otherwise, malicious payloads will bypass your inspection pipeline and compromise downstream application servers. Finally, we apply routing intent to enforce traffic flow across the fabric. This ensures that all internet-bound traffic is routed through the firewall for inspection before leaving your environment. You define destinations and the next hop resource ID explicitly. Forgetting to attach intent policies causes traffic to leak directly to the internet, breaking your security posture and triggering compliance violations. Here is the Azure CLI command to create a routing intent policy. We specify the resource group and hub name, then set destinations to internet, and point the next hop to the firewall resource ID. This forces traffic through the firewall automatically. Running this without verifying subnet CIDRs will cause routing conflicts that drop legitimate user packets across all connected regions. When designing your virtual WAN, follow these best practices to maintain a stable production environment. Use secured hubs for compliance requirements to ensure consistent security policies across all regions. Plan your IP addressing carefully to avoid overlaps with on-premises networks, which causes silent routing failures. Optimize latency by placing hubs near users, and enable branch-to-branch connectivity to bypass expensive MPLS lines. Remember this key principle for your certification exam. Centralization reduces operational overhead. By consolidating networking, security, and routing into a single global fabric, you simplify management and improve scalability across your enterprise. Skipping this consolidation forces you to patch individual route tables manually, which inevitably leads to configuration drift and prolonged outage times during emergency maintenance windows. Let us check your understanding with a quick scenario. In a virtual WAN design, how do you control traffic flow through the hub? You cannot modify route tables directly through the portal interface. Instead, you must use routing intent to define destinations and next hops for inspection. Choosing manual peering instead will create asymmetric routing loops that severely degrade application performance during peak business hours. We covered the global transit concept that powers virtual WAN and defined the hub as a managed connectivity point. We compared VWAN to traditional models, highlighting automation benefits. We designed a secured hub with firewall and routing intent using Terraform and CLI. Finally, we reviewed best practices like IP planning and latency optimization, ensuring you avoid costly misconfigurations during your actual deployment phase. For the AZ-305 exam, focus on these critical tips to maximize your score. Know that virtual WAN reduces gateways and simplifies routing across complex multi-region topologies. Understand secured hubs and how firewall standard integrates with routing intent policies. Be able to identify when to use VWAN versus traditional peering for hybrid workloads. Remember that you cannot modify hub route tables directly, so always apply intent policies instead. Imagine sending a confidential document through a crowded market where anyone could read it. A VPN gateway acts like an armored courier service that wraps your data in an unbreakable shield before it hits the public internet, ensuring only the intended recipient can access it. In this lesson, we will explore how to design these secure tunnels for hybrid cloud environments. You will learn to configure Azure VPN gateways with IKEv2 encryption and verify MTU limits to prevent silent packet drops that break production workloads. We will start by reviewing the core architectural patterns for site-to-site and point-to-site connections. Then, we will dive into a procedural guide for implementing high availability and encryption. Finally, we will cover critical configuration parameters and common pitfalls to avoid on your exam. You will configure VPN gateway ZRS resources for zone redundancy, apply strong IKEv2 policies, and validate routing tables to prevent misconfigured subnets from dropping legitimate traffic during failover events. A VPN gateway is the bridge between your private network and the public internet. It uses ISEC protocols to create an encrypted tunnel, ensuring confidentiality and integrity. Modern gateways support dynamic scaling, allowing you to handle varying traffic loads without dedicated lines like MPLS. This approach balances security with cost efficiency for hybrid architectures. You must select the appropriate SKU tier, such as VPN-GW3, to guarantee sufficient throughput. Otherwise, your applications will experience severe latency or timeout errors during peak usage hours. Site-to-site connects entire networks, like a corporate office to a cloud VPC. Point-to-site connects individual clients, such as remote workers accessing internal tools. Understanding this distinction is crucial for selecting the right gateway type and client configuration requirements. You will configure route-based connections using PowerShell or CLI commands, ensuring you assign correct address prefixes, because mismatched CIDR ranges will immediately break routing tables and isolate your cloud resources from on-premises systems. This comparison highlights the key differences between topology options. Site-to-site is ideal for branch offices and server access, requiring no client software on the user side. Point-to-site serves individual devices, often used for developers or administrators working remotely. Your choice depends on whether you need network-level or device-level connectivity. You must carefully map subnet CIDRs to avoid overlapping address spaces, because conflicting IP ranges will cause immediate routing conflicts and completely halt data synchronization across your hybrid infrastructure. We will now walk through the implementation workflow for a secure VPN design. First, we must select the appropriate topology and provision the gateways to establish the connection endpoints. You will deploy the primary gateway using the AZ Network VPN Gateway Create command, specifying the correct SKU and public IP allocation, because skipping this step leaves your hybrid link unestablished and exposes internal services to unauthorized external access. This Terraform configuration demonstrates the initial setup. We define the customer gateway to represent your on-premises firewall with its BGP-IES-N and public IP address. Next, we provision the virtual VPN gateway within your cloud VPC to handle the termination point. Finally, we establish the connection resource that links these two gateways using IPsec and static routing. You must verify the shared key complexity and enable IKEv2 protocols. Otherwise, weak authentication will trigger immediate session drops during certificate validation failures. With the topology established, we move to the second step. You must configure strong encryption parameters and enable perfect forward secrecy to protect session keys. You will apply the PFEs Group 1 parameter for maximum compatibility while enforcing IEE's 256GCM ciphers, because failing to enforce these standards leaves your data vulnerable to cryptographic attacks and violates strict compliance auditing requirements during security assessments. The final step involves validating the MTU settings and routing protocols. Adjusting the MT U prevents fragmentation issues, while BGP enables dynamic route updates for resilience. You will explicitly set the virtual network gateway MTU to 1,350 bytes, because ignoring this adjustment causes packet fragmentation that silently drops large database queries and breaks application connectivity across your hybrid environment. This configuration snippet shows how to harden the tunnel parameters. We set the maximum transmission unit to 1,350 bytes to prevent fragmentation issues caused by VPN headers adding extra overhead. Then, we enable Border Gateway Protocol to allow dynamic route updates, ensuring your network adapts automatically if paths change. You must verify the BGP peer state remains established, because a stale routing table will cause persistent connectivity failures during primary link outages and disrupt critical business operations. A tunnel is only as secure as the keys protecting it. Always prioritize modern encryption standards and regular key rotation in your design. You will configure automated certificate expiration alerts and enforce minimum key lengths of 2,000 bits, because neglecting proper key management allows attackers to decrypt captured traffic and compromises sensitive organizational data during routine security audits. Visualize the data flow through your VPN. Traffic originates from an on-premises subnet and hits the customer gateway. The IPsec tunnel encrypts the packets before they traverse the public internet. The cloud gateway decrypts the traffic and routes it into the target VPC subnets, completing the secure handoff. You must verify private IP ranges do not overlap with your cloud CIDR blocks, because address conflicts will cause routing loops that completely halt data replication and disrupt synchronized application states. Let's check your understanding. What is the most common cause of hanging VPN connections where small packets work but large file transfers fail? Consider the impact of headers on packet size. The answer is MTU mismatch causing fragmentation drops. You must adjust the tunnel MTU to 1,350 bytes and verify the underlying physical interface supports larger frames, because ignoring this threshold causes silent packet loss that breaks database transactions and stalls critical deployment pipelines. We covered the essential aspects of VPN gateway design. You learned to select between site-to-site and point-to-site topologies based on your use case. We implemented a secure configuration workflow, emphasizing encryption standards and MTU validation. Finally, we reviewed best practices like BGP for dynamic routing and monitoring for tunnel health. You must document all CIDR assignments and verify gateway skew limits before production deployment, because skipping these checks causes immediate connectivity failures and violates strict compliance auditing requirements. For the AZ-305 exam, focus on high availability design patterns like active-active gateways. Be prepared to identify CIDR overlap issues as a critical failure point. Remember that key rotation is a security requirement, and always verify MTU settings when troubleshooting connectivity issues. You must configure VPN GW3 as resources for zone redundancy and validate BGP peer states using the AS network VPN connection show command, because misconfigured routing tables will cause exam scenario failures and disrupt critical production workloads. Imagine a highway where traffic slows down during rush hour and anyone can merge into your lane. That is exactly what the public internet looks like for critical enterprise data. ExpressRoute builds an exclusive, private tunnel straight to Azure, bypassing congestion and keeping your information safe from public exposure. You will avoid unpredictable latency spikes and potential data leaks that happen when traffic traverses shared networks. This dedicated path guarantees predictable performance for your mission workloads. In this lesson, we will explore how to design a robust ExpressRoute solution for your enterprise environment. We cover connectivity models and SKU tiers, peering configurations, designing with Terraform, and the best practices that keep your network reliable. You need to understand these components because misconfiguring peering can cause routing loops or break access to Azure storage accounts. Mastering these details ensures you pass the certification exam and deploy production-ready architectures confidently. ExpressRoute provides a private connection between your on-premises infrastructure and Azure. Unlike site-to-site VPN, which tunnels traffic over the public internet, ExpressRoute uses a dedicated link managed by your service provider. This ensures predictable performance, enhanced security, and high availability with strong SLAs. You must choose this path for latency-sensitive applications because public routing introduces jitter that breaks real-time databases and causes compliance failures during audits. When designing your circuit, you must choose the right connectivity model and tier carefully. Local SKUs restrict access to the nearest Azure region only, while standard allows access across a single geopolitical boundary. Premium is strictly required for global connectivity and increased route limits up to 4,000 prefixes. Choosing the wrong tier will immediately block cross-region replication and trigger unexpected billing charges from your cloud provider. Peering defines exactly how your circuit connects to Azure services at the network layer. Azure Private Peering links directly to your private IP space and virtual networks. Microsoft Peering connects specifically to public Azure services, such as blob storage and SQL database. You must assign the correct peering type, because mixing them up will prevent your application from resolving service endpoints and break authentication flows entirely. Data flows from your on-premises router through the dedicated physical link directly to the Microsoft Edge router. From that Edge node, it routes through your configured peering settings straight into your virtual network. The flow remains strictly private, ensuring low latency and high throughput for heavy workloads. If you misconfigure the BGP advertisements, traffic will black hole and cause immediate service outages for your users. First, select your connectivity model based entirely on where your physical hardware resides in your data center. If you are located inside an authorized colocation facility, you must use the Cloud Exchange colocation model. This approach requires you to provision a cross-connect directly into the Microsoft Edge device. Failing to verify facility authorization will delay provisioning by several weeks and halt your entire migration timeline. If your hardware sits inside a facility that hosts a Microsoft peering location, you must formally request a cross-connect through your service provider. This setup uses the Cloud Exchange colocation model to establish direct physical access to our network edge. You need this configuration because shared internet gateways cannot guarantee the throughput required for enterprise database replication or backup operations. Next, you must carefully choose your tier and SKU before provisioning the resource group. Local SKUs strictly limit access to the nearest Azure region only, while standard allows broader access across a single geopolitical boundary. Selecting an incorrect tier will immediately restrict traffic routing and cause your applications to fail when they attempt to reach secondary regions for disaster recovery. For a standard SKU, you receive access to all Azure regions located within a single geopolitical boundary. You must upgrade to the premium tier if your architecture requires global connectivity and increased route limits beyond 4,000 prefixes. Choosing the wrong tier will block cross-border replication and force you to recreate the circuit, which incurs significant provisioning delays and extra costs. Finally, you must explicitly configure peering on the newly created circuit resource. Azure Private Peering connects directly to your virtual networks and private IP spaces. Microsoft peering connects specifically to public Azure service endpoints like storage and SQL database. Skipping this configuration step will leave your circuit completely inactive and prevent any traffic from reaching your cloud resources. Configure Azure Private Peering to securely link your circuit to your designated private IP space. You must run the AZ network ExpressRoute peering, create command, and set the peer IES-N number. Specify exact address prefixes for each BGP session carefully. Using incorrect prefix ranges will cause route conflicts and break connectivity to your virtual network gateways, which immediately halts all production traffic. Redundancy remains completely non-negotiable in modern cloud architecture design. You must always provision at least 2 separate circuits across different physical paths to protect against hardware failure or fiber cuts. Relying on a single connection will create a critical single point of failure that violates enterprise SLAs and causes immediate service outages during routine maintenance windows. Consider which peering type actually connects your circuit to public Azure services like blob storage and SQL database. The correct answer is Microsoft peering, not private peering. You must select this option because private peering only routes traffic to virtual networks. Choosing the wrong type will break authentication flows and prevent your applications from accessing managed database endpoints entirely. Core best practices include designing for strict redundancy using dual circuits across separate physical paths. You should actively use BGP communities to influence outbound routing decisions and monitor circuit health continuously with Azure Monitor metrics. Implementing BFD is essential because it provides sub-second failure detection, preventing packet loss during automatic failover events and keeping your applications online. Use Terraform alongside the AZ network ExpressRoute circuit create command to reliably provision your ExpressRoute connection. You must define the resource group name, target location, and specific service provider in your configuration file. Configure the SKU tier and private peering with secure BGP keys and exact address prefixes to prevent routing conflicts across environments. We thoroughly covered connectivity models, SKU tiers, peering configurations, and Terraform implementation strategies. You must remember to design strictly for redundancy using dual circuits, actively use BGP communities for traffic control, and monitor your circuits closely with diagnostic logs. Ignoring these practices will lead to unmanaged routing loops, unexpected billing spikes, and prolonged downtime during critical production incidents. For the certification exam, you must focus heavily on peering types and exact SKU differences between tiers. You need to clearly know when to use private versus Microsoft peering for specific workload requirements. Remember that downgrading bandwidth often requires deleting and recreating the entire circuit, which causes extended downtime and will definitely appear in performance-based exam scenarios. Imagine a high-security building with multiple checkpoints where every visitor is verified against a list before entering. That is exactly how network security groups protect your cloud infrastructure. In this lesson, we will design NSGs that secure your applications while keeping them accessible. You will learn the mechanics, build a 3-tier architecture, implement rules using code, and master certification best practices. Mastering these controls prevents unauthorized access during real-world breaches, ensuring your AZ-305 exam questions align perfectly with Microsoft security standards. We start by exploring how NSGs evaluate traffic using the 5-tuple and priority system. Next, we will design a secure 3-tier architecture with granular rules for web, application, and database tiers. Then we move to infrastructure as code using Azure CLI commands to automate these rules. Finally, we cover best practices and common pitfalls to avoid on the exam. Understanding this flow prevents misconfigured rules that could accidentally expose production databases to public IP ranges. A network security group acts as a stateless virtual firewall that filters inbound and outbound traffic to cloud resources within a virtual network. It contains security rules that allow or deny traffic based on source, destination, port, protocol, and direction. You apply these rules directly to subnets or network interfaces using the Azure portal. This setup provides the Zero Trust Foundation for securing your applications and databases while preventing accidental exposure of critical endpoints. Traffic flows through an NSG using a strict evaluation process. First, the packet enters the virtual network and hits the NSG attached to the subnet or NIC. The system extracts the 5-tuple containing source IP, destination IP, ports, protocol, and direction. Next, rules are sorted by priority, with lower numbers evaluated first. Finally, the first matching rule determines whether the traffic is allowed or denied. Missing a priority number causes evaluation failures that block legitimate application communication. Let's design a secure 3-tier architecture. We start with the web tier, which handles public traffic. This tier must allow inbound HTTP and HTTPS from the Internet while restricting outbound access to internal services only. You will assign priority 100 to these rules using the Azure CLI. Failing to restrict outbound traffic allows compromised web servers to communicate directly with malicious command and control endpoints during an active breach. This rule allows HTTPS traffic from the Internet to the web subnet. We assign priority 100 to ensure public access is permitted early in the evaluation process. The destination port is set to 443 for secure web traffic, while the source address prefix remains wildcard to accept any client. Setting an invalid priority number causes conflicts with system, deny rules that could accidentally lock out legitimate administrators during deployment. Next is the app tier. This layer processes business logic and must never be directly accessible from the Internet. We restrict inbound traffic to only the web tier subnet, ensuring that only authorized requests reach the application servers. You will configure this using a specific service tag named Virtual Network. Skipping this restriction exposes your backend services to brute force attacks that compromise sensitive user credentials. Here we restrict inbound traffic to port 8080, but only from the web tier subnet CIDR. This ensures the app tier receives requests solely from the web layer. By specifying the source address prefix as the web subnet, we prevent external access while allowing internal communication. Using a wildcard source instead of a specific IP range opens your application ports to public scanning tools. Finally, the database tier is locked down. This tier stores sensitive data and must only accept connections from the app tier. We allow inbound traffic on the database port from the app subnet and deny all outbound traffic to prevent data exfiltration. You will apply this using a priority 200 rule with an action set to deny. Overlooking outbound restrictions allows attackers to exfiltrate customer records directly to external storage accounts. This rule allows Postgres traffic on port 5432 from the app tier subnet. We deny all outbound traffic to prevent unauthorized updates or data leaks. By restricting both inbound and outbound access, we ensure the database tier remains isolated and secure. You will verify this configuration using the Azure CLI command list. Failing to explicitly deny outbound traffic creates a critical gap that permits lateral movement between compromised virtual machines. When designing NSGs, you must choose between subnet level and NIC level placement. Subnet level offers high security granularity with low management complexity, making it the recommended approach for most architectures. NIC level provides very high granularity but increases management complexity significantly. Always prefer subnet level unless you need per VM isolation. Attaching rules to individual network interfaces creates hundreds of duplicate configurations that become impossible to audit during compliance reviews. This Terraform resource defines a rule named Allow HTTPS Inbound. We set the priority to 100, ensuring it executes before any deny rules. The direction is inbound, targeting TCP port 443. By specifying the source as Internet, we allow public web traffic while keeping the subnet secure. This code ensures your security rules are version-controlled and reproducible. Omitting the priority field triggers a default value of 5,000 that overrides critical access controls. Always adopt a deny-by-default posture to secure your cloud environment. This means explicitly allowing only the traffic required for your application to function, while blocking everything else. This principle reduces the attack surface and ensures that only authorized access reaches your resources. You will enforce this by placing system rules at priority 5100. Ignoring this default behavior exposes every endpoint to unfiltered scanning tools. Test your understanding of priority. Which rule takes precedence if a priority 100 allow and priority 200 deny conflict? The priority 100 allow rule wins because lower numbers are processed first. Always remember that NSGs evaluate rules in ascending priority order, so the first match determines the action. Misordering these values causes unexpected connectivity failures that break production deployments. NSGs are stateful firewalls, meaning they automatically allow return traffic for established connections. This reduces the number of required rules by up to 50% compared to stateless designs. You only need to define inbound rules. The NSG handles the outbound response automatically. Additionally, use application security groups to group VMs by function instead of IP addresses. Forgetting this stateful behavior forces you to write redundant rules that complicate your architecture. We covered NSG mechanics, three-tier design, ISC implementation, and best practices. Remember that NSGs are stateful firewalls for VNets. Apply NSGs at the subnet level for best management. Use ISC to enforce consistent security rules. Always adopt a deny-by-default posture. These principles will help you secure your cloud infrastructure effectively. Mastering these configurations prevents costly compliance failures and ensures you confidently answer scenario-based questions. Focus on priority order and stateful behavior for the exam. Know when to use subnet versus NIC-level NSGs based on granularity needs. Understand default rules and their limitations, especially the deny all inbound rule. Master ISC for NSG deployment in exams, as you may need to identify misconfigurations in code snippets. Reviewing these concepts prevents critical scoring penalties and ensures you correctly troubleshoot network connectivity issues. Imagine a high-tech customs checkpoint at a major international airport where every vehicle and passenger is inspected against a master list before passing through. In the cloud, your virtual network demands that exact same scrutiny. Azure Firewall acts as your managed security gateway, automatically scaling to handle traffic spikes while blocking malicious payloads. If you skip this perimeter control, unfiltered traffic will flood your resources, exposing sensitive data and triggering compliance violations during audits. We will start by exploring the core architecture of Azure Firewall and its key features like threat intelligence feeds. Then we will look at how Firewall Manager centralizes control across multiple subscriptions using policy assignments. Next, we will walk through a step-by-step implementation using the Azure CLI to provision resources efficiently. Finally, we will cover traffic flow patterns and critical exam pitfalls that frequently trip up candidates during performance-based questions. Azure Firewall is a fully managed, cloud-native network security service operating at the edge of your virtual network. It leverages a hub-and-spoke architecture, where the firewall resides in a central hub VNet to inspect traffic between spokes, on-premises networks, and public endpoints. This design guarantees high availability across 3 availability zones while scaling automatically from 1 to 20 SUs based on demand. Misconfiguring the routing table will cause asymmetric routing failures and drop legitimate user requests. Stateful inspection is a critical concept you must master for the certification exam. Unlike basic packet filters that examine headers only, this mechanism tracks the context of active connections by maintaining a dynamic session table. It verifies that return packets match an established session and automatically drops unsolicited inbound traffic. Failing to configure proper state tracking will allow unauthorized lateral movement and expose internal databases to external scanning attacks. Azure Firewall offers 3 distinct tiers to match your exact security requirements. The basic tier provides core application and network filtering without intrusion detection. Standard adds threat intelligence feeds and fully qualified domain name filtering for web traffic. Premium unlocks the intrusion detection and prevention system, along with TLS inspection for deep packet analysis. Selecting the wrong tier will leave sensitive workloads exposed to known exploits and fail strict compliance audits. Let's walk through the implementation process step by step. First, you must create a dedicated subnet with the exact name Azure Firewall Subnet to host the firewall resource inside your hub network. This naming convention is strictly enforced by the platform and cannot be customized. Using any other subnet identifier will trigger a deployment failure and halt your entire infrastructure provisioning pipeline until you correct the configuration. We use the Azure CLI to create this subnet efficiently. The command specifies the resource group and VNet name while setting address prefixes to a 26 range. This allocation provides exactly 60 usable IP addresses for internal requirements and management endpoints. Running out of available addresses will prevent automatic scaling and force you to manually resize the network, causing unnecessary downtime during peak operational hours. Next, we deploy the firewall resource itself using a precise configuration block. We define the name, location, and SKU to ensure it runs in VNet mode within our designated hub. The platform requires explicit routing table updates immediately after provisioning. Skipping this step will cause outbound traffic to bypass inspection entirely, leaving your applications vulnerable to unfiltered external threats and violating baseline security policies. The CLI command creates the firewall in the East US region with specific parameters. We specify the SKU as AZFW VNet to enable strict VNet integration and link it directly to the subnet we just created. This parameter triggers the underlying platform to allocate dedicated management endpoints automatically. Forgetting this flag will default to classic mode, which breaks modern hub-and-spoke architectures and prevents centralized policy enforcement. Finally, we configure network rules to control outbound traffic flow precisely. We create a collection that allows internal TCP traffic on port 480 from our source range to the destination address. Rule collections require explicit priorities ranging from 1 to 6,555. Assigning duplicate priorities will trigger a validation error and block all subsequent rule evaluations until you resolve the conflict. This command defines a network rule collection with precise source and destination parameters. It allows TCP traffic from the 10.0.0.0.16 source to reach the destination address on port 80. The priority of 100 ensures this rule is evaluated early in the chain before any deny-all statements. Misordering priorities will cause legitimate application requests to be dropped unexpectedly, breaking connectivity for downstream services. Traffic flow relies heavily on user-defined routes to direct packets correctly. When a spoke VNet sends traffic to the internet, UDRs redirect that traffic to the firewall's private IP as the next hop. The firewall inspects the packet, applies rules, and forwards it through the gateway subnet. Responses return through the same path while maintaining state. Incorrect route priorities will cause asymmetric routing and trigger connection timeouts. Security is only as strong as your most permissive rule in any network design. Always follow the principle of least privilege by restricting rules to specific IPs and CIDRs rather than using broad allow-all statements. Explicitly defining port ranges and protocol types prevents accidental exposure. Leaving default deny rules misconfigured will allow unauthorized administrative access and trigger immediate security alerts during compliance scans. Let's check your understanding with a quick scenario question. What is the specific subnet name required to deploy an Azure firewall successfully inside a hub network? If you use a different name, what happens during provisioning? The platform strictly rejects custom identifiers and returns a validation error. This hard requirement ensures consistent routing table generation and prevents accidental bypass of security inspection policies across your environment. We covered the core architecture of Azure Firewall and its hub-and-spoke model for centralized inspection. We explored the tier differences, including standard threat intelligence and premium TLS capabilities. We implemented a firewall using CLI commands to provision subnets and configure rule collections. Finally, we reviewed traffic flow with UDRs and key best practices for secure network design that directly impact certification exam performance. For the AZ-305 exam, focus heavily on firewall tiers and their specific feature sets. Remember that subnet naming is mandatory and cannot be customized for production deployments. Understand how UDRs direct traffic to the firewall private IP address using explicit next-hop configurations. Firewall manager policies allow centralized governance across multiple subscriptions, preventing misconfigured routing tables from exposing critical workloads to external threats. Imagine a sudden flash flood rushing toward a small bridge. Without reinforced pillars and diversion channels, the structure collapses under the weight of the water. Running a production application without DDoS protection is exactly like that bridge. Azure DDoS protection acts as the engineered defense system that absorbs the surge and protects your infrastructure. Without this service, your virtual network becomes vulnerable to volumetric floods exceeding 1 gigabit per second, causing immediate downtime and triggering costly auto-scaling events that drain your budget before you notice the breach. We will start by comparing the two protection tiers and their specific use cases. Next, we will look at how traffic flows through the service and how mitigation happens automatically. Then, we will walk through a bicep implementation to link your virtual network to a protection plan. Finally, we will cover essential best practices for monitoring, defense in depth, and common pitfalls to avoid on the exam. Skipping this sequence often leads to misconfigured networks that fail penetration tests or trigger unexpected billing spikes during traffic spikes. Azure DDoS Protection is a managed service designed to defend your Azure resources against large-scale distributed denial of service attacks. It works by continuously monitoring traffic patterns and applying adaptive tuning based on your application's unique baseline. While Azure provides always-on infrastructure protection for free, the DDoS Network Protection tier adds tailored tuning, real-time analytics, and dedicated support for enterprise-grade defense. Failing to enable this tier leaves your public endpoints exposed to volumetric floods that can easily saturate your bandwidth and crash your backend services. Understanding the two tiers is critical for design decisions. DDoS IP protection is a consumption-based option ideal for small to medium workloads, protecting individual public IP addresses with standard mitigation capabilities. In contrast, DDoS network protection is designed for enterprise-scale environments. It protects entire virtual networks, offers advanced tuning through Azure Monitor integration, and provides dedicated support engineers during an active attack. Choosing the wrong tier often results in either overspending on unused capacity or suffering prolonged downtime when attackers target your core infrastructure. Let's compare these tiers side by side to clarify when to use each. IP protection focuses on individual resources and scales with usage, making it cost-effective for smaller footprints. Network protection covers the entire VNet scope, includes advanced analytics via log analytics, and adds a fixed monthly fee plus per IP charges. For most AZ-305 scenarios involving public-facing applications or critical infrastructure, network protection is the recommended design choice. Misapplying IP protection to a multi-service environment leaves your internal subnets unprotected during coordinated volumetric attacks. Here is how the traffic flow works under attack. Inbound traffic hits the Azure Edge network first. The service analyzes the packet volume against your learned machine learning baseline. If the traffic exceeds the threshold, the mitigation engine activates at the edge. Malicious packets are dropped before they reach your resources. Legitimate traffic passes through to your application, ensuring availability is maintained throughout the event. Skipping this automated filtering process allows malicious payloads to consume your compute instances and trigger costly scale-out operations. Now let's implement DDoS protection using infrastructure as code. The first step is creating the DDoS protection plan resource itself. This plan acts as a container for your protection policies and must be created before you can link it to any network resources. You would typically run as network DDoS protection plan create in Azure CLI, specifying a region like East US2. Neglecting this prerequisite step causes deployment failures when your bicep templates attempt to reference an undefined plan identifier. This bicep snippet shows how to define the plan and link it to a virtual network. We start by declaring the protection plan with a name and location. Next, we define the virtual network with its address space. Inside the Properties block, we set Enable DDoS Protection to True and reference the plan's ID to establish the link. This single configuration activates defense for every public IP within this VNet. Forgetting this flag leaves your load balancer exposed to SYN flood attacks that exhaust connection tables. With the plan and VNet linked, we move to the second step. You must ensure that all public-facing resources within the VNet are properly associated with the protection plan. This includes application gateways, public load balancers, and Azure Bastion hosts. The service automatically extends protection to any new public IP created in this scope. Overlooking these specific gateway configurations leaves critical ingress points unprotected, allowing attackers to bypass your firewall and directly target your backend subnets. This example demonstrates the monitoring configuration you should add to your infrastructure. We define a diagnostic settings resource that streams logs to a log analytics workspace. The DDoS protection analytics category captures attack metrics and mitigation events. By routing this data, you enable real-time alerting and forensic analysis for your security team. Ignoring this telemetry setup prevents you from detecting slow-rate application layer attacks, which often go unnoticed until your IPI endpoints return 50 server errors. The final step is configuring monitoring and alerts. Enabling the service alone is insufficient for a robust design. You must set up Azure Monitor alerts to notify your team when mitigation thresholds are reached. Additionally, integrate with Microsoft Sentinel for advanced threat hunting and automated response playbooks. Failing to configure these notifications means you will only discover an active volumetric attack after your virtual machines have already crashed and your SLI penalties begin accruing. This configuration block shows how to simulate attacks for validation. We use an approved testing partner service to send controlled traffic against your public endpoints. This step validates that your alerting rules trigger correctly and that mitigation engages as expected. Regular simulations ensure your incident response procedures are tested before a real attack occurs. Skipping these scheduled tests leaves you guessing whether your WAF integration will actually drop malicious packets or simply queue them until latency spikes. This principle reminds us that DDoS protection handles the flood, while WAF handles the intruder. Designing for resilience requires a layered defense strategy where network-level volumetric attacks are mitigated by DDoS protection, and application layer threats are blocked by web application firewall. Relying on a single service leaves gaps in your security posture. Without this dual approach, attackers can easily bypass your firewall using simple HTTP floods that exhaust your compute resources before your rules even evaluate the payload. Let's check your understanding. Which Azure service is primarily responsible for mitigating Layer 7 application-specific attacks, such as HTTP floods or SQL injection attempts? Is it DDoS protection, WAF, or a network security group? The correct answer is the Web Application Firewall, which inspects request headers and payloads at port 4043. Choosing NSGs instead leaves your API endpoints vulnerable to credential stuffing attacks that easily bypass standard network rules. We covered the two tiers of DDoS protection and compared their features for design decisions. We walked through a bicep implementation to link a VNet to a protection plan and configured monitoring for visibility. Finally, we emphasized defense in depth with WAF integration and the importance of regular attack simulations. Always design your infrastructure to be resilient by default. Neglecting these foundational steps guarantees that your architecture will fail under sudden traffic surges or coordinated volumetric assaults targeting your public endpoints. For the AZ-305 exam, focus on design decisions that balance cost and protection. You may encounter scenarios asking you to recommend IP protection versus network protection based on workload size and budget. Remember that DDoS protection only covers public IP addresses. Private resources rely on NSGs and ASGs. Always look for answers that include monitoring integration and defense in-depth strategies. Overlooking these constraints typically leads to selecting overly expensive tiers for simple web apps or missing critical exam points about subnet isolation. Imagine sending a confidential package via the public mail system versus using a dedicated courier van that stays entirely on private roads. In cloud architecture, we face this exact choice every day. Public endpoints expose your services to the internet, introducing massive risk. Azure Private Link solves this by routing traffic through the Microsoft backbone using specific private IPs. Let's explore how to design and implement this secure connectivity for your next certification exam. We will start by defining the core anatomy of Private Link and its network interface components. Next, we will compare service endpoints against private endpoints to clarify when to use each during an exam scenario. Then, we will walk through a hands-on implementation using Terraform to provision these resources in a production subscription. Finally, we will cover critical DNS configurations and security best practices to ensure your design passes the AZ-305 review without losing points on connectivity failures. A private endpoint is a network interface created within your virtual network that assigns a private IP address from your VNet space to a PAS resource. This NIC acts as the gateway, allowing your applications to communicate with services like Azure SQL or blob storage directly over the Microsoft backbone. You must configure it carefully because misassigning an IP range causes subnet exhaustion and breaks application connectivity during peak traffic hours. We rely on Private Link primarily for security through strict isolation. When you attach a private endpoint, 100% of the traffic traverses the Microsoft backbone network inside their secure data centers. This means your sensitive customer data never leaves the infrastructure to hit the public internet. It also simplifies networking by removing complex firewall rules or public IP management for your managed services, preventing accidental exposure during routine maintenance windows. Visualize the exact data flow moving through your architecture. Your application resides in a specific subnet within your VNet and sends a request to a storage account. Instead of routing out to the public internet, the traffic hits the private endpoint network interface card. This NIC links directly to the storage account private link service using a dedicated backend pool. The connection establishes over the backbone, ensuring data remains isolated throughout the journey. It is crucial to distinguish between service endpoints and private endpoints during your exam preparation. While both provide secure paths, they operate completely differently under the hood. Service endpoints keep the public IP but restrict traffic via route tables pointing to Microsoft backbone routes. Private endpoints assign a private IP within your VNet subnet. For AZ-305, remember that private endpoints offer stronger isolation because they remove the public endpoint entirely when configured correctly. Now let's implement this architecture using a proven 3-step procedure to provision a private endpoint via infrastructure as code. First, we create the private endpoint resource itself and link it directly to your target subnet. This establishes the network interface and connects it to the PAS resource backend. Failing to attach the correct subnet ID will cause deployment failures and leave your application unable to reach the service securely. Here is the Terraform code for that first critical step. We define an Azure private endpoint resource and specify the subnet ID where the NIC will reside inside your production workspace. Inside the private service connection block, we link the endpoint to the storage account ID and specify the subresource name as blob. This creates the secure tunnel interface, but forgetting the exact subresource name will trigger a validation error during deployment. Next, we integrate the DNS configuration to complete the setup. A private endpoint remains completely useless if your application cannot resolve the private IP address correctly. We must link the endpoint to a private DNS zone group inside your network configuration. This ensures that when your app queries the storage FQDN, it receives the exact private IP instead of the public one, preventing connection timeouts during peak load. In this code block, we configure the DNS integration using a private DNS zone group reference. This block points directly to your private DNS zone ID, which contains the exact record mapping the storage account FQDN to the assigned private IP. Without this group properly linked to the subnet, name resolution will fail immediately, breaking all application connectivity and causing widespread service outages across your environment. Finally, we disable public network access on the PAS resource to lock down the environment. This is the critical security step that prevents unauthorized access. Once the private endpoint is verified and DNS resolution works perfectly, you must turn off the public endpoint on the storage account firewall settings. This ensures that even if someone discovers the public URL, they cannot reach the data without being inside the VNet. Here is the configuration to disable public access using a simple Boolean flag. In the storage account resource block, we set public network access to false. This effectively removes the public endpoint from the network interface entirely. The only way to access the storage now is through the private endpoint we created earlier, enforcing strict network-centric security and preventing accidental data exposure during routine deployments. Remember this principle: DNS acts as the bridge that makes private link actually work in production. You can create the endpoint and disable public access, but if DNS resolution fails entirely, your application cannot connect to the service. Always verify that your VNet is linked to the private DNS zone and that records are populated correctly before moving to the next environment stage. Let's check your understanding with a practical scenario. Suppose you create a private endpoint for a SQL database, but you forget to disable public network access on the database firewall itself. What is the security implication? The correct answer is that the database remains reachable via its public IP address, undermining the security benefits of the private link and leaving sensitive data exposed to external threats. To recap, private endpoints provide secure access to PAS resources by assigning private IPs within your VNet subnet space. We compared service endpoints to private endpoints, noting the superior isolation of the latter during exam scenarios. We implemented a solution using Terraform, covering NIC creation, DNS integration, and disabling public access. Finally, we emphasized that DNS configuration remains critical for reliable connectivity across all workloads. For the AZ-305 exam, focus heavily on these specific points during your study sessions. You will likely see questions about DNS resolution failures. Always check VNet links to private DNS zones before selecting an answer. Remember that service endpoints do not provide private IPs. Also, note that private endpoints consume IP addresses from your subnet, so monitor address space availability carefully to prevent deployment bottlenecks. Imagine you're driving a car at night without headlights. That's what running production without reliable name resolution looks like. In cloud architecture, DNS acts as your traffic control system, translating human-readable names into IP addresses machines need to communicate. Without a robust DNS strategy, your applications become invisible and hybrid connections fail instantly. Today, we will architect a resilient DNS solution, using Azure's native services to keep your infrastructure visible and secure. We begin by distinguishing between public DNS for internet-facing domains and private DNS for secure internal resolution within virtual networks. Next, we execute the exact CLI commands to provision a private DNS zone and link it to your VNet. We will then analyze hybrid connectivity patterns using the Azure DNS private resolver with inbound and outbound endpoints. Finally, we address critical certification pitfalls regarding TTL optimization and our back permissions to prevent unauthorized record modifications. Azure DNS is a high-performance hosting service for DNS domains running on the Microsoft Azure Infrastructure. It provides authoritative name resolution using the same Entra ID credentials and REST APIs as your other cloud resources. This integration allows you to manage domain records alongside VMs and databases directly in the Azure portal or via PowerShell, ensuring consistent governance across all your infrastructure components without switching contexts. Azure offers 3 distinct DNS components tailored to specific architectural needs. Public DNS manages internet-facing domains with global Unicast routing. Private DNS resolves names exclusively within your virtual networks, keeping traffic off the public internet. The Azure DNS private resolver bridges on-premises environments and Azure VNets through managed inbound and outbound endpoints, eliminating the operational burden of maintaining custom VM-based forwarders while ensuring scalable name resolution. Let's configure a private DNS zone to secure internal access for an Azure SQL database. We start by creating the zone resource itself using the AZ network private DNS zone create command. This establishes the namespace where we will store internal records. For example, we define the zone as DB, private, contoso, com within the ProdRG resource group located in Eastus, ensuring the scope matches your organizational structure. This script initializes the private DNS zone by defining variables for the resource group and location to keep the command clean. The AZ network private DNS zone create command provisions the zone named private, contosa, com. This creates the namespace where we will store our internal records. Using variables like rgname and location streamlines the process, allowing you to reuse the script across multiple subscriptions efficiently. Now that the zone exists, we must link it to our virtual network using AZ network private DNS link VNet create. This step makes the DNS service active for resources inside that VNet. We enable auto-registration with registration enabled true, so VMs automatically register our records when deployed. This automation reduces manual maintenance and ensures new instances are immediately discoverable by other services in the network. Here we link the zone to the target VNet using the command with registration enabled true. This flag is crucial. It allows Azure to automatically create a records for VMs deployed in this network. For example, when you deploy a web server, its IP address registers instantly. This reduces manual maintenance and ensures new instances are immediately discoverable by dependent services without administrator intervention. Finally, we add the actual DNS records using AZ network private DNS record seta add record. For a SQL database, we need an A record that maps the hostname to the private IP address of the database server. This command creates the specific endpoint mapping required for applications to connect securely. We specify the record set name and the target IP to ensure accurate resolution. This command creates an A record named SQLDB within the zone with IP 10005 and a TTL of 3600 seconds. The full command looks like AZ network private DNS, record seta add record gprodrgz private, contoso, com n SQLDB a 10005. This record ensures that any query for SQLDB, private, contoso, com resolves to the correct internal database endpoint, enabling seamless connectivity for your applications. When designing hybrid architectures, you must choose between the managed Azure DNS private resolver and traditional VM-based DNS. The table compares their operational characteristics. Notice how the resolver eliminates management overhead while providing superior scalability compared to maintaining your own forwarders. The managed service offers pay-as-you-go pricing and automatic updates, whereas custom VMs require patching and capacity planning for high availability. In a hub-and-spoke topology, we centralize DNS governance within the hub virtual network. The diagram shows how spoke VNets link to the hub's private DNS zones using delegation or VNet links. This creates a single source of truth for name resolution across the entire subscription. By linking spokes to the hub, you ensure every spoke resolves names consistently without duplicating zone configurations in each network. This principle guides our design. Centralize governance to maintain consistency across all environments. When DNS is distributed across multiple unmanaged servers, configuration drift and resolution errors become inevitable as updates are missed. A centralized hub ensures every spoke resolves names identically using the same private DNS zones. This approach simplifies auditing and guarantees that failover mechanisms rely on accurate, synchronized record data. Let's check your understanding with a scenario. You are deploying a critical service that requires frequent failovers between primary and secondary endpoints. You set the TTL to 86,400 seconds, which equals 1 full day. What is the primary risk of this configuration? Consider how long clients will cache the old IP address before updating their local resolver after a manual or automated switch occurs. The answer is prolonged downtime during failovers. High TTLs like 86,400 seconds delay propagation significantly. For active failover scenarios, keep TTLs low, around 60 seconds, to minimize client cache duration. Other pitfalls include ignoring our back. Without reader and contributor roles, unauthorized users could modify records and hijack traffic. Always verify VNet links if resolution fails, as missing links break name resolution entirely. We have mastered the essentials of Azure DNS architecture. You distinguished between public DNS for internet domains and private DNS for internal VNet resolution. You executed steps to set up a private DNS zone with links and records using CLI commands. You explored hybrid patterns using the Azure DNS private resolver and hub-and-spoke design. Finally, you identified critical pitfalls regarding TTL optimization and our back security controls. For the AZ-305 exam, focus on distinguishing between private DNS zones and the Azure DNS private resolver. Know that the resolver manages inbound and outbound endpoints for hybrid connectivity scenarios involving on-premises networks. Expect questions testing VNet link configurations and auto-registration features. Always select managed services over VM-based solutions unless legacy constraints force otherwise, as exams prioritize scalable, low-management architectures. Imagine a highway system where every car has to take the longest possible route to reach its destination, and traffic lights are completely random. That is exactly what happens to your users when network performance and routing are poorly designed. In this lesson, we will explore how to keep data moving fast and reliably by mastering latency, throughput, and intelligent traffic routing strategies. If you skip proper configuration, application response times will spike past acceptable thresholds, causing customer churn and triggering automatic scaling penalties that drain your cloud budget overnight. Here is what we will cover. We start by distinguishing between latency and throughput, the two metrics that define user experience. Next, we look at global routing strategies like GSLB and Anycast. Then we walk through a step-by-step design process for high-performance routing. Finally, we discuss protocols and edge optimization to keep your infrastructure snappy. Mastering these concepts directly impacts your ability to pass performance architecture questions on the certification exam, and neglecting them will cause unpredictable failover behavior during actual deployment windows. Let's start with the fundamentals. Latency is the time it takes for a packet to travel from source to destination, usually measured in round-trip time or RTT. Throughput is the volume of data moved in a given time period. As an infrastructure designer, your goal is to minimize latency by reducing physical distance and hops, while maximizing throughput by ensuring sufficient bandwidth and efficient protocols. Confusing these two values will lead you to over-provision expensive network interfaces when you actually need faster geographic placement, causing budget waste and degraded application responsiveness. Traffic routing is the mechanism that directs data across the most efficient paths. It ensures reliability and speed by intelligently selecting where traffic goes based on geographic proximity, server health, or load conditions. Understanding this concept is crucial for designing solutions that meet strict performance SLAs. If you misconfigure routing weights or ignore endpoint health probes, your load balancer will continuously send requests to failing instances, triggering cascading timeouts and violating the 99.9% availability targets required for production workloads. To manage these metrics effectively, we employ various routing strategies. GSLB directs users to the closest geographic data center, significantly reducing latency. Anycast routing uses a shared IP address across multiple nodes, letting BGP metrics route traffic to the nearest node. CDNs cache static assets at the edge, offloading traffic from the origin server entirely. Mixing these up during an exam scenario will cause you to select the wrong service for dynamic database queries, leading to unnecessary cross-region egress fees and degraded user experience. Now let's design a high-performance routing solution. We will follow 3 key steps. First, we define latency targets based on user expectations. Second, we select the appropriate global strategy to meet those targets. Finally, we implement health checks and optimization to ensure resilience. Skipping the initial requirement gathering phase will result in over-engineered network topologies that fail automated compliance audits and introduce unnecessary routing loops during peak traffic events. For the second step, selecting a global strategy, we can use Terraform to define a latency-based routing record. This configuration directs users in the US East 1 region to a specific endpoint. The latency routing policy block ensures that Route 53 evaluates the user location and routes traffic to the nearest healthy region automatically. Running as network DNS record, set a list without verifying TTL settings will cause stale DNS propagation, forcing clients to connect to deprovisioned endpoints during active maintenance windows. With the strategy selected, we move to the next phase. We must define our latency targets clearly and then select the global strategy that aligns with those requirements. This ensures that every routing decision supports the overall performance goals of the application. Failing to document these thresholds explicitly will lead to ambiguous SLI reporting, making it impossible to troubleshoot bottlenecks when packet loss exceeds the acceptable 5% threshold during high concurrency events. Visualizing the traffic flow helps us understand how data moves through our infrastructure. In a CDN-enabled architecture, the user request first hits an edge node. If the content is cached, it returns immediately. If not, it fetches from the origin server and caches for future requests. This flow minimizes latency for repeat users. Misconfiguring cache TTL values will cause excessive origin pull requests, overwhelming your backend compute resources and triggering automatic throttling during sudden traffic spikes. Finally, we implement health checks and optimization. This involves defining our latency targets, selecting the global strategy, and then ensuring that traffic is only routed to healthy endpoints using automated health probes. We also optimize protocols to handle packet loss gracefully. Neglecting probe interval configuration will cause delayed failover detection, leaving active connections stranded on unhealthy nodes and violating your established recovery time objectives during planned maintenance cycles. To implement weighted distribution, we can configure a load balancer using Nginx. The upstream block assigns weights to backend servers, sending more traffic to powerful instances and less to smaller ones. The proxy pass directive then routes requests to this weighted pool, ensuring efficient load distribution. Setting incorrect weight values will starve lower capacity VMs of resources while overloading primary nodes, causing uneven response times and triggering false positive health check failures across your deployment tier. Remember this key principle. Always aim to terminate connections as close to the user as possible. By utilizing edge functions, you can perform authentication or header manipulation before the request even hits your primary infrastructure, drastically reducing latency. Implementing this correctly will cut average response times below 200 milliseconds, while ignoring edge termination forces all traffic through centralized gateways, creating single points of failure that crash under moderate concurrent load. Let's check your understanding. Which metric measures the time it takes for a packet to travel from source to destination, and which strategy uses a shared IP address to route traffic to the nearest node? Think about the definitions we covered. Answering these correctly demonstrates mastery of core networking concepts, while mixing them up during the certification exam will cost you immediate points on performance architecture questions that require precise terminology matching. To recap, we explored how latency and throughput define network performance. We compared routing strategies like GSLB, Anycast, and CDNs to manage traffic efficiently. We designed a high-performance routing solution by defining targets, selecting strategies, and implementing health checks. Finally, we optimized protocols and edge caching to ensure resilience. Mastering these implementation details will directly improve your score on practical design scenarios, while overlooking probe configurations will cause cascading service failures during actual production deployments. For the AZ-305 exam, focus on distinguishing between latency and throughput metrics. Be prepared to choose the right routing strategy based on geographic distribution requirements. Remember that health checks are essential for automated failover, and always consider edge caching to reduce origin load. Practice identifying the best solution for high-performance network designs. Failing to memorize specific CLI parameters and service capabilities will result in incorrect architecture selections when evaluating complex multi-region deployment scenarios under strict time constraints. Think of exposing your VMs to public or DP ports like leaving your office front door unlocked and expecting a security guard to catch every intruder. In the cloud, automated bots scan for credentials in milliseconds. Azure Bastion closes that door completely by routing management traffic through the Azure backbone. You simply click Connect inside the portal without ever opening port 22 or 3389. This prevents credential stuffing attacks and keeps your production environment compliant with zero trust principles, avoiding costly breaches from exposed endpoints. We will start by examining the critical risks of exposing virtual machine endpoints directly to the internet. Next, we will analyze how Azure Bastion proxies are DP and SSH traffic through a managed gateway inside your virtual network. Then, we will execute actual CLI commands using AZ-Network Bastion Subnet Create and AZ-Network Bastion Create. Finally, we will master the exact NSG rules and exam scenarios that prevent connectivity failures during certification exams. Traditional remote management forces you to open ports 22 and 3389 on your network security groups. This creates a massive attack surface for automated brute force attempts and continuous port scanning. Azure Bastion solves this by operating as a fully managed platform-as-a-service gateway deployed directly inside your virtual network. It routes browser-based SSL connections straight to private endpoints, eliminating public IP requirements and removing the need to manually configure complex, inbound security rules for administrative access. Azure Bastion is a fully managed platform-as-a-service that delivers secure, RDP and SSH connectivity directly through the Azure portal interface. It establishes an encrypted SSL tunnel between your browser and the target virtual machine, guaranteeing that administrative traffic never touches the public internet. This architecture removes the requirement for custom Bastion host agents or third-party, remote desktop clients, which drastically reduces configuration drift and prevents unauthorized access failures during critical maintenance windows. The data flow begins when you click Connect inside the Azure portal from your local browser. The Bastion service, deployed directly in your virtual network, acts as a managed reverse proxy. It establishes an encrypted tunnel and forwards RDP or SSH packets straight to the private IP address of your target virtual machine. This architecture guarantees that all administrative traffic remains strictly within the Azure backbone, preventing exposure to external threats and avoiding accidental public endpoint leaks. We will walk through the deployment process using a cumulative approach that builds each component logically. First, you must create a dedicated subnet named Azure Bastion subnet with a minimum 26 address prefix. Second, you provision a standard SKU public IP and link it to the Bastion host resource. Third, you configure strict NSG rules to allow gateway traffic. Skipping any step breaks the tunnel and forces you to expose your virtual machines to untrusted networks. You must provision a standard SKU public IP resource named My Bastion Public IP before creating the host. Then you deploy the Bastion resource using as network Bastion create, explicitly linking the gateway to your virtual network and the newly created public endpoint. This sequence establishes the exact infrastructure required to handle encrypted tunnels. If you skip the SKU requirement or mismatch the subnet reference, the deployment fails immediately and leaves your management plane unprotected. You must configure inbound NSG rules on the dedicated subnet to allow traffic from Gateway Manager and Azure Load Balancer service tags on port 44.3. This configuration ensures the Bastion service can communicate correctly with core Azure infrastructure and successfully route your administrative sessions. If you omit these specific service tags, the gateway cannot authenticate requests, causing immediate connection timeouts and forcing you to temporarily expose your virtual machines to untrusted networks. We implement these steps using as network VNet subnet, create with the exact name Azure Bastion subnet, and a 26 prefix of 10.0.10.26. Next, we provision the standard SKU public IP using as network public IP create in the East US region. Finally, we deploy the Bastion host by specifying the resource group, virtual network reference, and the exact public IP address to establish the secure tunnel. Misconfiguring the prefix size breaks the service entirely. NSG rules are absolutely critical for Bastion to function correctly. You must explicitly allow inbound traffic from Gateway Manager and Azure Load Balancer service tags on port 44.3 to the dedicated subnet. Outbound, you must permit the Bastion subnet to communicate with target VM subnets on ports 22 and 3389. Without these exact rules, the gateway cannot authenticate your session, causing immediate connection failures and forcing you to expose endpoints publicly. Let's check your understanding with a critical deployment pitfall. A common error occurs when engineers misspell the subnet name during configuration. What is the exact casing and spelling required for Azure Bastion to deploy successfully? You must type Azure Bastion subnet precisely without extra spaces or alternate capitalization. Getting this wrong triggers immediate validation failures, blocks the entire gateway provisioning process, and wastes valuable lab time during certification assessments. Remember this core architectural principle for your design. Secure access begins by completely eliminating the public attack surface from your virtual networks. By deploying Bastion, you guarantee that all management traffic is encrypted over SSL and authenticated through Azure ID conditional access policies. This approach prevents credential harvesting attacks and ensures compliance with zero-trust frameworks without exposing any administrative ports to external threats. We covered the essential features of Azure Bastion today. You learned that it eliminates public IP requirements on virtual machines by providing secure portal-based access through a managed gateway. We walked through the exact deployment sequence using CLI commands and subnet configurations. Finally, we reviewed the precise NSG rules required to allow gateway manager traffic and ensure reliable connectivity without exposing administrative endpoints to untrusted networks. For the AZ-305 exam, focus strictly on these scoring points. You must memorize that the subnet name requires exactly Azure Bastion subnet with a minimum 26 prefix size. Remember that production environments require the standard SKU to enable features like secure file transfer and multi-factor authentication. You also need to recall that you never manage NSG rules for remote access traffic, but you must explicitly allow Gateway Manager inbound to pass scenario questions. Imagine you are moving a house without taking an inventory of your furniture. You might pack boxes blindly, lose important items, or rent a truck that is far too small for what you actually own. That is exactly what happens when you lift and shift workloads to the cloud without a structured plan. Azure Migrate solves this by acting as your central hub for discovery, assessment, and migration. It tracks every server into Azure. Without this visibility, you risk deploying undersized virtual machines that crash under production load or overspending on premium storage tiers you never need. In this lesson, we will explore the core components of Azure Migrate, walk through the critical assessment process step by step, review industry best practices for sizing and licensing, examine common pitfalls to avoid, and wrap up with key takeaways tailored for your AZ-305 certification exam. We will specifically examine how to deploy the Migrate appliance across VMware clusters, calculate exact CPU utilization thresholds using the performance methodology, and identify misconfigured network rules that break dependency mapping. Mastering these details ensures you can confidently architect secure cloud migrations during both exams and production deployments. Azure Migrate is not a single tool, but a suite of integrated services that simplify the entire lifecycle. The process begins with discovery, where you identify every server and application in your current environment. Next comes assessment, which determines if your workloads are ready for the cloud and calculates exactly what they will cost. Finally, migration executes the actual movement of data and compute using tools like Azure Site Recovery. Automating dependency mapping reduces risk significantly, while performance-based sizing can slash your monthly bill by up to 40% compared to raw on-premises hardware. Skipping this sequence often leads to orphaned resources and unexpected egress fees that drain your budget. Before you can assess anything, you need a way to see what is running. The Azure Migrate appliance is an OVI file for VMware or a VHD for Hyper-V that you deploy directly inside your data center. It acts as the bridge between your physical infrastructure and the cloud portal. By communicating securely with your hypervisor, it inventories your servers without requiring you to log into every individual machine manually. You must assign at least 2 vCPUs and 8 GB of RAM to ensure accurate performance sampling. Failing to meet these requirements will cause incomplete CPU metrics and force you to restart the discovery cycle. Let us walk through the assessment process step by step. First, you deploy the appliance in your on-premises environment to begin inventorying your servers. You must configure the appliance to point directly to your Azure Migrate project workspace and ensure outbound port 443 traffic is allowed through your corporate firewall. This initial handshake establishes a secure channel for streaming performance metrics back to the cloud. If you misconfigure the network rules, the portal will display pending status indefinitely and delay your migration timeline by several weeks. While you can manage everything through the portal, using the Azure CLI gives you precise control over your migration projects. The first command retrieves detailed information about an existing project within a specific resource group. The second command lists all assessments currently tracked inside that project, allowing you to verify discovery status and review readiness reports before proceeding. For example, running AZ-Migrate project show against your RG migration group workspace instantly reveals whether dependencies are fully mapped. This automation prevents manual portal clicks from causing configuration drift during large-scale enterprise rollouts. Next, we enable dependency analysis on the appliance. This installs the Microsoft monitoring agent on your servers to track active network connections. Grouping servers into logical applications ensures you do not accidentally migrate a web server while leaving its backend database behind. You must explicitly define port ranges such as 3389 for SQL traffic and 1221 for HTTPS endpoints. Missing these specific ports will break the dependency map and cause critical application failures immediately after cutover. When you create an assessment report, Azure Migrate provides sizing recommendations based on historical usage. You can choose between different strategies depending on your goals. As on-premises simply mirrors your current hardware specs for a quick lift and shift. Performance-based leverages historical CPU and memory usage to right-size your resources. Application-centric uses dependency mapping data to group multi-tier applications logically before assigning compute targets. Selecting the wrong methodology often results in over-provisioned D-series virtual machines that waste budget or under-provisioned B-series burstable instances that throttle during peak business hours. Finally, you generate the assessment report directly in the Azure portal. This report provides a readiness score indicating if servers are ready or need conditions addressed. It breaks down monthly cost estimates and suggests specific VM SKUs based on your historical performance data. You should export these findings as CSV files to track baseline metrics across multiple migration waves. Ignoring the readiness warnings frequently causes deployment failures when Azure attempts to provision incompatible operating system versions or unsupported disk configurations. Keep this principle in mind as you plan your migration. A common mistake is assuming that an initial assessment remains accurate forever. It is strictly a point-in-time recommendation based on the data collected during discovery. Always rerun your assessment 48 hours before the actual cutover to account for any recent changes in your on-premises infrastructure. Failing to refresh these metrics after adding new batch processing jobs will cause severe performance bottlenecks and trigger automatic scaling limits that disrupt end-user access during critical business operations. To ensure a smooth assessment, follow these industry standards. Run your discovery appliance for at least 7 to 14 days to capture cyclic workloads like weekend backups. Always calculate the impact of the Azure Hybrid Benefit toggle before presenting a final budget, as it can reduce licensing costs by up to 40%. Grouping servers by application tier ensures that latency-sensitive communication is maintained within the same availability zone. Skipping these validation steps frequently leads to unexpected hybrid cloud compliance audits and severely inflated monthly compute invoices. Dependency mapping relies on structured data collection rather than guesswork. The appliance first collects the initial hypervisor inventory from your vCenter or Hyper-V hosts. The monitoring agent then tracks active network connections between those servers using standard TCP and UDP port definitions. This data flows securely into the Azure Migrate service, which finally generates a visual dependency map so you can see exactly how your applications communicate. Misconfigured proxy settings often block this telemetry stream and force you to manually reconstruct complex application architectures from scattered log files. Let us pause and check your understanding. How long should you run the Discovery appliance to ensure you capture all cyclic workloads like end-of-month processing? The answer is at least 7 to 14 days. This duration prevents you from undersizing your Azure resources based on incomplete data. You must verify that performance metrics consistently reach 95% utilization across all measured intervals before finalizing your VM SKU selections. Failing to meet this threshold will result in burstable B-series instances, throttling during peak load, and causing critical application timeouts. We have covered the essential components of Azure Migrate. Centralize your discovery and assessment in one hub to avoid manual scripts. Prioritize performance-based sizing over as on-premises configurations to maximize cost efficiency. Map dependencies before migrating multi-tier applications to prevent broken flows. Finally, always validate the hybrid benefit impact on your final budgets before presenting them to stakeholders. Mastering these precise configuration steps ensures you can accurately calculate monthly compute costs and confidently defend your architectural decisions during certification assessments and production reviews. For the AZ-305 exam, focus on knowing the 3 distinct phases of migration and the specific purpose of each. Understand how the appliance deploys differently for VMware versus Hyper-V environments. Recognize how the hybrid benefit directly impacts your cost estimates in the assessment report. Finally, identify scenarios where you must rerun assessments before a production cutover to account for infrastructure changes. You should practice calculating exact CPU thresholds using the performance methodology and memorize the required port ranges for SQL and HTTPS traffic to quickly eliminate incorrect answer choices. Imagine you're moving to a new home without packing boxes or finding the keys. You would end up stranded outside or carrying furniture into storage rooms. That is exactly what happens when you attempt cloud migration without rigorous assessment. In this lesson, we will discover your infrastructure using Azure Migrate, map dependencies, and build a strategy that works before touching production workloads. Skipping this phase causes costly downtime and breaks critical application links. Here is our plan for the lesson. We will start with the fundamentals of discovery using tools like Azure Migrate and Dependency Agent. Then we dive into dependency mapping and migration strategies tailored for AZ-305 scenarios. Finally, we walk through a complete assessment workflow to tie it all together. Mastering this sequence prevents unexpected downtime during cutovers and ensures you can confidently answer exam questions about workload categorization and risk mitigation. Successful discovery splits into 2 parallel streams. First, you gather technical inventory by capturing CPU, RAM, storage, and network throughput metrics from your on-premises environment using the Azure Migrate appliance. Second, you map dependencies to see how applications talk to each other via port 443 or SQL endpoints. Without this data, you risk migrating a database while leaving its application server behind, which breaks connectivity and triggers costly rollback procedures during exam scenarios. Let's define a critical risk term, migration drift. This happens when the infrastructure you actually deploy differs from what was assessed and approved during planning. It causes costs to balloon because you are paying for unused capacity and it introduces security vulnerabilities by leaving legacy configurations untouched. For example, deploying an unapproved standard D4's v3 instance instead of a validated B2S type breaks compliance audits and triggers unexpected monthly billing spikes that fail certification reviews. This configuration outlines a tiered migration strategy for an e-commerce platform. The web tier is marked for rehosting to Azure Kubernetes Service, while the database tier uses replatforming to Azure SQL Database. Notice how the affinity groups keep dependent services together, ensuring they move as a single unit to minimize latency. Skipping this grouping causes cross-region traffic fees and breaks session state management during peak holiday shopping events. You will need to categorize every workload using the official 6RS framework. Rehost is a straightforward lift-hand shift using Azure Migrate. Replatform makes minor cloud optimizations like switching to managed SQL. Refactor rewrites code for cloud-native features such as serverless functions. Repurchase replaces with SaaS, retain keeps on-prem, and retire discards unused assets. Misclassifying a Tier 1 database, as retire causes catastrophic data loss during certification assessments. First, we discover the current state by running automated scans to capture hardware specs and software versions across your entire estate. You will deploy the Azure Migrate appliance to collect CPU counts, memory allocations, and disk throughput metrics. Failing to baseline these metrics leads to severe performance bottlenecks when you migrate heavy workloads into improperly sized virtual machine scale sets during live production cutovers. This Python script validates connectivity to critical dependencies before migration. It iterates through a list of host and port pairs, checking if the target endpoints are reachable via socket connections. A successful connection confirms that the network path is open and ready for traffic. Skipping this validation causes silent DNS failures that halt deployment pipelines and trigger expensive recovery operations during certification lab exercises. Next, we map dependencies by analyzing network flow logs and application traffic patterns to identify which systems rely on each other. You will enable Azure Network Watcher flow logs on your virtual networks to capture bidirectional traffic metadata. Missing these dependency maps causes accidental isolation of critical microservices during subnet migrations and breaks compliance reporting for regulated financial workloads. Here, we use a Terraform import block to map existing cloud resources into our state file. This command pulls the configuration of live infrastructure into code, giving you a clear picture of your current dependencies and eliminating shadow IT surprises. For instance, running Terraform import Azureum resource group. Demo rgprod data immediately syncs your state with actual Azure Resource Manager definitions, preventing conflicting updates during exam scenarios. Then, we right-size targets by analyzing performance baselines to provision smaller, cost-effective cloud instances based on actual usage rather than allocated capacity. You will review Azure Monitor metrics for average CPU utilization and memory pressure over a 30-day window. Over-provisioning these workloads wastes budget and triggers unnecessary scaling events that degrade application response times during peak transaction periods. This JSON block shows a right-sizing recommendation generated from discovery data. It compares the on-premises allocation against actual peak usage, suggesting a smaller instance type that meets performance needs while reducing monthly costs. For example, downgrading an oversized standard D8's v3 to a validated standard D4's v5 cuts compute bills by 40% without dropping database query throughput below acceptable SLI thresholds. Finally, we validate connectivity by running pre-migration scripts to ensure all network paths and firewall rules are correctly configured for the target environment. You will execute enslookup commands against private DNS zones and verify NSG allow rules for ports 80 and 443. Ignoring these checks causes silent packet drops that halt deployment pipelines and trigger expensive rollback procedures during certification assessments. This bash script performs a final connectivity check against the target cloud endpoints. It uses a simple TCP handshake to verify that ports are open and responsive, confirming that the migration pipeline is ready for traffic. For instance, running curl so dev/null https://prod_ip.cloudapp.net immediately verifies TLS termination and routing health before you cut over production workloads during exam labs. Quick check: which strategy involves making minor cloud optimizations without rewriting the core application code? The answer is replatform. You would choose this approach when migrating an on-premises SQL Server to Azure SQL Managed Instance to leverage automated patching and built-in high availability. Mastering this distinction prevents costly re-architecting expenses and directly aligns with AZ-305 workload migration scoring criteria. Remember this principle: successful migration is 80% planning and 20% execution. If the assessment phase feels long, it means you are doing it right. You will spend weeks validating dependency maps and right-sizing virtual machines before executing a single as VM create command. Rushing this stage causes cascading failures that violate SLI commitments and trigger expensive emergency rollback procedures during live cutovers. To recap, discovery must be data-driven using automated tools, dependency mapping prevents broken connections, right-sizing saves money by matching instances to actual usage, and starting small with pilot projects validates your strategy before mass migration. You will leverage Azure Migrate for inventory, Network Watcher for flow logs, and Monitor for baseline metrics. Applying these steps systematically eliminates guesswork and ensures predictable certification exam outcomes. For the exam, focus on knowing the official 6Rs of migration, understanding how to prevent migration drift through strict approval gates, planning for right-sizing based on 30-day baselines, and validating connectivity early in the process. You will encounter scenario questions requiring you to select Azure Migrate appliances for inventory and verify NSG rules before cutover. Mastering these details guarantees you pass the workload assessment domain on your first attempt. Imagine you're planning a cross-country move for a large family. You wouldn't just throw furniture into a truck and hope it fits at the destination. You'd inventory your items, pack carefully, hire professional movers, and then organize everything in your new home. Cloud migration works the same way. Without a structured plan, you risk data loss, budget overruns, and security gaps. The Azure Cloud Adoption Framework gives you that blueprint, turning a chaotic move into a repeatable, scalable process. Here is what we will cover in this lesson. We start with the CIF strategy and its 3 core phases. Then we dive into the 5Rs to help you choose the right migration path for each workload. Next, we look at landing zone essentials, which form the foundation of your cloud environment. Finally, we wrap up with exam focus points and common pitfalls to watch for. Let's define the core term you need to master. The Azure Cloud Adoption Framework, or CIF, is Microsoft's prescriptive guidance for cloud adoption. It provides a proven set of best practices, documentation, and tools designed to help organizations achieve their business objectives. CIF aligns your business, people, and technology strategies, ensuring that migration is not just a technical lift, but a strategic business enabler. Now we execute the migration lifecycle. This is a multi-step process that moves you from assessment to optimization. We will walk through each phase and see how they build upon each other to ensure a successful migration. In the assessment phase, you must verify your network readiness before moving any workloads. This PowerShell snippet demonstrates checking a virtual network subnet capacity. We retrieve the VNet object and iterate through its subnets to display the address prefix. This ensures you have sufficient IP space allocated in your landing zone before deploying migration agents. Once assessment is complete, we move to the migration phase. Here, you establish your landing zone, which provides the identity, connectivity, and governance foundation. This step ensures that every workload lands in a secure, governed environment rather than an unmanaged subscription. Setting up the landing zone requires creating resource groups with governance tags from the start. This bash command creates a new resource group and applies environment and owner tags. These tags are critical for identity management and cost tracking, ensuring that every resource deployed later inherits the correct governance structure. The final phase is optimization. Migration does not end when the application runs in Azure. You must refine performance, monitor costs, and enforce security compliance. This involves implementing tools like Azure Cost Management and Azure Policy to continuously improve your environment. To optimize cost, you can enforce governance rules using Azure Policy. This JSON defines a custom policy that audits resources missing a cost center tag. By enforcing this rule, you ensure that every workload is tagged for budget accountability, preventing untracked spend and helping finance teams manage their cloud investments effectively. When planning your migration, you must rationalize your inventory using the 5Rs. This table compares each strategy based on effort and cloud benefit. Rehost is the fastest, but offers minimal cloud benefits. Refactor adapts code for PaaS services. Rearchitect modifies code for cloud-native features. Rebuild rewrites from scratch, while replace swaps to a SaaS solution. Right-sizing is a critical part of the optimization phase. On-premises servers are often over-provisioned, leading to wasted spend. By using Azure Migrate assessment reports, you can downsize CPUs and RAM to match actual usage patterns. This practice typically reduces your monthly cloud bill by 30 to 50%, delivering immediate value from your migration. Your landing zone topology dictates how data flows between your on-premises environment and Azure. This diagram shows a hub-spoke model. Traffic enters via ExpressRoute to the hub VNet, which hosts shared services like DNS and firewalls. From there, traffic routes to spoke VNets where workloads reside, ensuring isolation and secure communication. Let's check your understanding. Which migration strategy involves rewriting an application from scratch to leverage cloud-native capabilities? Think about the effort level and the degree of change required. Keep this principle in mind as you design your migration. Optimization is not a one-time event that happens after the move. It is a continuous loop that starts before the first byte moves and continues throughout the life cycle of your cloud environment. We have covered the essential elements of CIF for migration. You learned the 3 phases: assess, migrate, and optimize. We explored the 5Rs to help you choose the right strategy for each workload. We discussed landing zone essentials, including hub-spoke topology and governance tags. Finally, we emphasized right sizing and continuous optimization. For the AZ-305 exam, focus on identifying the correct migration strategy for given scenarios. You will likely be asked to choose between rehost and refactor based on business constraints. Remember that landing zone setup must precede workload migration. Also, watch for questions about Azure Migrate tools and cost optimization techniques like right sizing. Imagine you are moving a large house to a new city. You would never guess how furniture fits in the truck or risk breaking plumbing by guessing pipe locations. Instead, you hire a professional logistics team that plans every route and packs everything securely. Azure Migrate plays exactly this role for your cloud journey. It serves as your centralized hub to assess, migrate, and modernize on-premises workloads with minimal downtime. Skipping proper discovery risks orphaned resources and unexpected egress fees during cutover. We will start by exploring the Azure Migrate Hub architecture, then walk through the exact three-phase workflow required for successful cloud transitions. You will see a live VMware migration using the Azure Migrate PowerShell module, followed by critical best practices that directly impact your AZ-305 exam score. Understanding these phases prevents misconfigured network peering and ensures you can confidently answer scenario-based questions about workload modernization during the certification assessment. Let us define the core service precisely. Azure Migrate is a unified platform designed specifically for moving on-premises physical servers, VMware virtual machines, and SQL databases into Azure regions. It deploys lightweight discovery appliances to collect hardware metrics, generates detailed assessment reports for accurate DV3 series sizing, and orchestrates secure cutover execution. Failing to validate appliance connectivity often leads to inaccurate cost projections and unexpected performance bottlenecks during production transitions. The migration process follows a strict three-phase workflow that examiners expect you to master sequentially. First, you deploy an appliance or use agentless discovery to inventory your environment. Next, you run readiness checks and calculate optimal sizing based on CPU utilization thresholds. Finally, you execute the actual migration phase. Skipping dependency mapping between these phases frequently causes application timeouts and breaks critical database connections during production cutover. During discovery and migration, you must actively monitor replication health to prevent data loss. This PowerShell snippet retrieves server replication details and checks the sync status. You pass the resource group and project name to locate the appliance context, then query the specific server using gethas migrate replication protected item. Failing to verify the sync state property often results in incomplete block-level transfers and forces you to restart the entire replication cycle manually. Once discovery finishes, the workflow immediately shifts to assessment. Azure Migrate analyzes collected metadata to determine VM readiness, recommends optimal DES-v4 SKUs based on actual CPU utilization, and calculates precise monthly licensing costs. This data-driven approach prevents severe overprovisioning and controls cloud spend. Ignoring the assessment report frequently triggers budget alerts and forces architects to manually resize instances after deployment, which breaks existing application configurations. After assessment completes, you configure replication for the selected virtual machines. This PowerShell command initiates the replication policy and maps the on-premises disk to an Azure-managed disk. You specify the target storage account and replication policy using new AZ Migrate Replication Protection Container mapping to ensure data is block-level replicated securely. Misconfiguring the storage tier often causes replication lag exceeding the 15-minute threshold and triggers false failure alerts during the certification lab. The final phase is active migration. The appliance continuously performs block-level replication to your target region. Once synchronization reaches zero lag, you trigger a test migration to validate the application stack, followed immediately by the cutover where the source VM is permanently shut down and the Azure instance assumes production traffic. Skipping validation frequently causes DNS resolution failures and forces emergency rollback procedures that violate strict service-level agreements. Before going live, you explicitly invoke the cutover process to finalize the transition. This PowerShell command performs a final delta sync, shuts down the on-premises VM, and promotes the Azure instance to production using AZ Migrate replication protected item. You must resolve all external dependencies and verify network peering before executing this command. Forgetting to update application connection strings often results in immediate database lockouts and requires manual intervention during peak business hours. It is crucial to distinguish between test migration and cutover during certification reviews. Test migration creates an isolated clone within a dedicated subnet to verify application functionality without impacting the source environment. Cutover performs the final synchronization and switches production traffic, requiring the source VM to be permanently shut down. Confusing these steps frequently leads to accidental data corruption and violates strict compliance requirements for production workloads. For large-scale migrations, you must implement the migration factory approach to maintain operational control. Group servers into distinct waves based on business criticality and dependency mapping. Start with low criticality development and test environments to refine networking rules and validate authentication flows, then proceed to production workloads in subsequent waves. Neglecting wave planning often causes bandwidth saturation across your ExpressRoute circuit and triggers cascading service failures during peak operational hours. Remember this critical principle for your certification. Test migration acts as your mandatory validation step. Never skip the test phase, as network configurations like NSG rules and DNS records frequently differ between on-premises environments and Azure virtual networks. Testing ensures applications function correctly before you commit to cutover. Bypassing this verification routinely causes authentication failures and forces engineers to manually patch configuration drift during live production windows. Best practices require you to right-size virtual machines based on assessment reports to reduce monthly licensing expenses. You must utilize dependency analysis to accurately map server connections and validate application workflows before migration. Ensure your ExpressRoute bandwidth exceeds 1 Gbps to prevent replication bottlenecks. Always decommission on-premises VMs immediately after cutover to avoid unnecessary hybrid infrastructure costs and maintain strict compliance with cloud governance policies. Let us check your understanding with a quick certification scenario. When should you perform the final cutover? The correct answer is after successful test migration and final delta sync, ensuring the Azure VM is fully validated and ready for production traffic. Choosing to cut over prematurely frequently causes data inconsistency errors and violates strict minimum service level objectives that examiners specifically test during performance-based questions. We covered the Azure Migrate Hub architecture, the three-phase workflow of discovery, assessment, and migration, practical VMware steps using PowerShell CMDlets, and key best practices like right-sizing and dependency mapping. You must always execute test migration before cutover to validate network configurations. Mastering these sequential steps ensures you can confidently architect secure cloud transitions and successfully pass the technical validation required for professional certification exams. For AZ-305, focus heavily on the migration workflow phases and the specific purpose of each integrated tool. You must clearly distinguish when to use test migration versus cutover during scenario questions. Understand how dependency analysis maps application tiers for accurate placement. Expect performance-based questions on assessing VM sizing metrics and minimizing downtime during cutover procedures, as examiners prioritize practical cloud architecture decision-making skills. Imagine you are driving a heavy truck through a narrow tunnel blindfolded. Dropping your entire database into the cloud without validation guarantees a catastrophic crash. Azure Database Migration Service eliminates that risk by orchestrating schema mapping, data transfer, and validation automatically. You will use specific SKU tiers like Premium to handle large transaction logs safely. Skipping this structured approach means prolonged outages and corrupted records that are nearly impossible to recover without a comprehensive backup strategy. We will break down exactly how to transition your on-premises SQL Server workloads to Azure SQL Managed Instance using precise CLI commands. You will learn to calculate required vCore counts for the DMS instance based on your source throughput metrics. Understanding these architectural boundaries prevents connection timeouts during peak hours and ensures you can confidently answer scenario-based questions regarding maintenance windows versus continuous replication strategies. Azure Database Migration Service fundamentally separates workloads into offline and online migration modes based on your application downtime tolerance. Offline mode halts all write operations before copying static data, which works perfectly for batch reporting systems. Online mode executes an initial full load followed by continuous transaction log shipping to maintain synchronization. Choosing the wrong mode risks severe data loss or extended service interruptions that violate your agreed uptime SLI. The DMS instance serves as the core managed compute node responsible for orchestrating every step of your database transfer. You provision this resource using a specific SKU like Basic or Premium, depending on your data volume and network bandwidth constraints. This engine manages source connections, executes schema mapping commands, and maintains synchronization logs. Under-provisioning this compute tier will inevitably cause migration bottlenecks and trigger timeout errors during bulk transfers. The architecture routes your source database traffic directly through the DMS instance using either public endpoints or a self-hosted integration runtime for secure on-premises access. The service reads raw table structures and writes them to your target Azure SQL database while simultaneously capturing transaction log entries. This dual-path pipeline ensures data consistency during cutover. Failing to configure network rules properly will block port 1433 connections and halt the entire replication process. We will execute a complete online migration workflow by first deploying the compute node, then defining the migration project parameters, and finally validating synchronization metrics before switching application connections. This sequential approach guarantees that schema definitions align perfectly before actual data transfer begins. Skipping validation steps often results in mismatched data types or orphaned foreign key constraints that break your production application immediately after cutover. You can provision the service using the exact command as DMS instance, create resource group migration RG name DMS, instance 01 SKU basic, location Eastus 2. This CLI instruction establishes a single vCore compute node optimized for smaller database workloads under 500 gigabytes. Specifying the correct region minimizes network latency between your source and target endpoints. Misconfiguring the SKU tier will cause memory exhaustion and force the migration pipeline to abort unexpectedly. Configuring the migration project requires you to define precise endpoint connections for both your SQL Server source and Azure SQL target databases. You must explicitly select online data migration as the activity type to trigger continuous transaction log shipping instead of a static copy. This configuration establishes secure authentication channels and prepares the synchronization engine. Incorrectly selecting offline mode will prevent real-time log replication and force an extended maintenance window. You will structure your project definition using a JSON payload that explicitly maps source database names to target Azure SQL database schemas. The configuration must include the property migration type set to online data migration to activate continuous log capture. This precise mapping ensures that stored procedures and user-defined functions transfer correctly alongside raw table data. Omitting this property forces DMS into offline mode and breaks your planned zero downtime cutover strategy. You must actively monitor the migration dashboard to verify that the full load phase completes successfully before entering the continuous log sync stage. Tracking the data latency metric ensures your target database remains within a 5-second window of the source server. This vigilance prevents stale data replication and guarantees application consistency. Proceeding with cutover while latency spikes will cause transaction conflicts and corrupt your recently migrated records. You can verify migration progress using the PowerShell cmdlet getAZ DMS migration project to retrieve real-time status codes and replication metrics. This command explicitly shows whether the initial data copy has finished and if transaction log shipping remains active. Monitoring these exact states prevents you from switching application connection strings before synchronization stabilizes. Cutting over prematurely will result in missing records and force a complete rollback of your entire migration effort. Once your data transfer reaches completion and validation passes, you must immediately decommission the DMS instance using standard resource group deletion commands. Leaving this compute node active generates hourly billing charges for no operational value since it no longer processes replication tasks. Removing unused resources keeps your Azure subscription compliant with financial governance policies. Forgetting to terminate these services will steadily inflate your monthly cloud spend without delivering any business functionality. Offline migrations require you to halt source applications and execute static data copies, making them highly suitable for development environments with flexible maintenance windows. Online migrations maintain continuous transaction log replication, but demand rigorous monitoring of latency metrics and synchronization health. Selecting the appropriate strategy prevents unnecessary service interruptions during peak business hours. Misjudging your downtime tolerance will force emergency restarts and violate critical application performance agreements. You must treat the DMS instance strictly as a temporary migration bridge rather than a permanent infrastructure component. Many engineering teams overlook immediate decommissioning after cutover and accidentally accumulate hundreds of dollars in compute charges each month. Always execute as DMS instance delete commands immediately following successful validation. Neglecting this cleanup step violates cloud financial governance standards and creates unnecessary budget overruns for idle resources. Consider this scenario for your certification exam. Azure Database Migration Service automatically transfers schemas and table data, but it explicitly skips server-level configurations. You must manually recreate logins, SQL agent jobs, and cross-database dependencies using separate PowerShell scripts or maintenance plans. Overlooking these manual steps will break authentication flows and halt scheduled batch processing tasks. Mastering this distinction ensures you avoid common performance and connectivity pitfalls on exam day. We have successfully covered the complete database migration lifecycle using Azure Database Migration Service, from initial provisioning through final decommissioning. You learned to configure online replication, monitor latency metrics, and plan post-migration tasks like recreating SQL agent jobs. Always pair DMS with database migration assessment for accurate compatibility scoring. Ignoring these sequential steps will cause schema mismatches and force costly rework during your production cutover window. Focus heavily on distinguishing between offline and online migration strategies when answering scenario questions on your certification exam. Remember that DMS explicitly excludes SQL agent jobs and server-level logins from automatic transfer. You must select premium SKUs for databases exceeding 1 terabyte to prevent memory bottlenecks during bulk transfers. Understanding these exact boundaries ensures you can confidently troubleshoot replication failures and optimize cloud resource allocation. Moving your application to Azure App Service is like hiring a full-service hotel manager instead of maintaining your own home. You stop worrying about the plumbing, security, and cleaning, and focus entirely on delivering an excellent experience for your guests. This lesson guides you through migrating workloads to a fully managed platform that handles the heavy lifting. By offloading infrastructure management, you avoid costly downtime and security gaps while scaling efficiently using built-in auto-scale rules tied to CPU thresholds above 80%. We begin by evaluating migration strategies to select the optimal path for your existing codebase. Then we provision core infrastructure using standard Azure CLI commands like as-group create and as-appservice plan create. Next, we implement a zero-downtime deployment workflow leveraging staging slots for safe validation. Finally, we optimize your architecture for statelessness and security to prevent credential leaks and ensure reliable scaling during peak traffic windows. When migrating legacy workloads, you generally choose between a lift-and-shift approach or a comprehensive refactor. Lift and shift moves your application as is using tools like Azure Migrate, which is fast but often misses platform optimizations. Refactoring modifies the app to be stateless, externalizes sessions to Redis cache, and uses managed databases like Cosmos DB, unlocking true cloud scalability while preventing costly performance bottlenecks during sudden traffic spikes. Before migrating your workload, you must select the correct app service plan tier to match your operational requirements. Shared and basic tiers are cost-effective for development, but strictly lack production isolation and advanced networking features. Standard and premium tiers provide dedicated compute instances, enabling critical capabilities like auto-scaling across multiple VMs and deployment slots, which prevents accidental code rollouts from crashing your live environment. An app service plan acts as the foundational container for all your associated web apps and functions. It dictates the underlying compute resources, geographic location, and the specific features available to your application stack. You must define this plan before creating any web apps because misconfiguring the region or tier forces expensive data egress fees and breaks regional compliance requirements during audits. First, assess your current database dependencies and network configurations to ensure compatibility with cloud-native services. Then, provision the app service plan using a specific SKU like S1v3 within your designated resource group. This foundational step establishes the compute boundary and prevents accidental resource overlap that typically triggers billing surprises and deployment conflicts during active migration windows. We start by creating a resource group in EastUS using the as-group create command. Then, we define a standard tier plan named prod plan with as-appservice plan create to secure dedicated worker nodes. Finally, we create the web app using Node.js18lt ease runtime and configure the deployment credentials, which prevents authentication errors when pulling code from your Git repository. Next, deploy your application code to a dedicated staging slot to validate functionality without impacting live users. You create this isolated environment using the As web app deployment slot, create command with 2 slots total. This isolation prevents partial rollouts from corrupting production traffic and allows thorough load testing before committing any changes to the primary endpoint. We create the staging slot on the existing web app by appending the name ProdPlan Staging to your resource identifier. Then, we configure Git access for the slot using As web app deployment source config local Git. Finally, we push our local code repository to this remote staging environment, which guarantees that configuration drift and dependency mismatches are caught before they reach users. Finally, swap the validated staging slot to production, achieving a seamless cutover with 0 downtime. You execute this atomic operation using As web app deployment slot swap, which automatically handles warm-up periods and connection draining. This process prevents service interruptions by ensuring new instances are fully ready before routing live traffic away from the legacy environment. We execute the swap command to exchange the staging slot with the production slot using As web app deployment slot swap name ProdPlan resource group MyRG. The system validates the target configuration and performs an atomic switch that preserves environment variables. We verify the state is running smoothly after the transition, which catches misconfigured app settings before they trigger cascading failures in downstream services. Once migrated, you must optimize for security and reliability across every deployment pipeline. Externalize configuration using app settings to avoid hard-coded secrets that frequently leak through version control systems. Implement managed identities to authenticate with other services securely without storing connection strings in plaintext. Enable VNet integration if your app needs to access private backends, which prevents unauthorized public endpoint exposure during penetration tests. This flow illustrates a cloud-native architecture designed for high availability and rapid scaling. Requests hit the app service, which offloads session data to Redis cache and queries a managed database like Azure SQL. Ensuring instances remain stateless and interchangeable prevents data loss during automatic scale-out events, which would otherwise corrupt user carts and trigger severe transaction failures across your platform. Design your application to be stateless so that any instance can handle any request, ensuring seamless scaling and 0 downtime deployments. Store all user context in external stores like Azure Cache for Redis or Cosmos DB rather than local memory. This architectural discipline prevents session corruption during automatic restarts and guarantees consistent performance metrics across every scaled tier during peak examination scenarios. Let's check your understanding with a practical scenario. Which app service plan tier is required to use deployment slots and auto-scaling in a production environment? The correct answer is standard or premium tiers, as shared and basic plans strictly limit compute isolation. Recognizing this requirement prevents costly architectural mistakes during certification exams where misconfigured scaling rules frequently trigger performance degradation warnings. We covered the core pillars of migration that directly impact your certification success. You shift to PA-S to reduce infrastructure overhead, select robust plan tiers for reliability, use staging slots for safe cutover procedures, and externalize state for security compliance. Mastering these patterns prevents deployment failures during live traffic surges and ensures you confidently answer scenario-based questions about platform capabilities. For the exam, focus on IA-S versus PA-S distinctions to correctly assign workloads based on operational control requirements. Memorize tier capabilities regarding auto-scaling and slots, master C/LI commands for slot management, and identify VNet integration requirements for private resources. Understanding these boundaries prevents misconfigured networking answers that frequently fail candidates by overlooking subnet delegation rules and private endpoint dependencies. Imagine you are moving to a new house and packing every single item into one giant crate. You will struggle to fit it through the door and pay a fortune for oversized shipping. Containerization solves this by packing only what your application actually needs. For Azure certification, we use services like Azure Container Instances to deploy lean images without legacy bloat. If you bundle unnecessary OS packages, your deployment fails validation checks and incurs unexpected compute costs. Mastering this approach ensures your apps run efficiently across any cloud environment while shedding technical debt. We will cover the essential steps for migrating applications using containers. You will learn to decouple configuration from code using Azure Key Vault references, build optimized images with multi-stage builds, handle persistent data via Azure Blob Storage, and apply security hardening tactics. If you skip externalizing secrets, your credentials leak into image layers and trigger immediate compliance audits. We will walk through each phase systematically so you can confidently pass the migration assessment and deploy production-ready workloads without downtime or configuration drift. When you migrate legacy applications using a lift-and-shift strategy, you often end up with virtual machine sprawl. This means you are moving technical debt from an on-premises data center to expensive cloud VMs. Containerization solves this by providing environment parity. It ensures that your application behaves exactly the same way on a developer laptop running Docker desktop as it does in a production Azure Kubernetes service cluster, achieving 100% consistency across the lifecycle. If environments drift, you will encounter unpredictable runtime errors and fail certification scenario questions regarding deployment reliability. To successfully containerize an application, we follow a structured workflow. First, we must decouple configuration from the code to keep secrets safe using environment variables. Next, we write the Dockerfile blueprint that defines the runtime environment and base image. Finally, we optimize the image size by ignoring unnecessary files. If you hardcode connections strings directly into the source code, your deployment will fail security scans and expose sensitive database credentials to unauthorized network access during transit. Next in our workflow, we focus on the Dockerfile. This file acts as the blueprint for your image, defining the base OS and the commands to run your app. After that, we add a Docker ignore file to keep the image lightweight by excluding local logs and Git folders. You should explicitly list node modules and Git directories in that ignore file to prevent bloating the final artifact. Skipping this step will drastically increase pull times and trigger storage quota limits in your Azure Container Registry. Finally, we optimize the image using a Docker ignore file. This step is crucial for migration because it reduces the attack surface and speeds up deployment times by ensuring only essential files are included in the final container. You must run the command Docker build tappv1 to verify layer caching works correctly before pushing to production. If you skip this optimization, your image will exceed the 2 GB size limit and cause network timeouts during automated pipeline deployments. Let's look at a concrete example of a Docker file for a Node.js application. We start by using an official lightweight Alpine runtime to keep the image small. We set the working directory and copy package files first to leverage Docker layer caching. Then we install dependencies, copy the rest of the code, expose port 3000, and define the command to run the server. If you forget to pin the exact version number in your package, JSON file, your builds will break unexpectedly when upstream repositories update their dependency trees without warning. When migrating legacy applications, you must understand the concept of ephemeral storage. Ephemeral storage refers to the temporary file system inside a container that is destroyed when the container stops or restarts. This means any files written locally will be lost, so you must design your application to store persistent data in external databases or object storage instead. If you save session tokens directly to the local disk, those records will vanish during pod rescheduling and cause immediate authentication failures across your cluster. Use this checklist to guide your migration phases. Start with assessment to identify dependencies like OS libraries and network ports. Move to preparation by externalizing configurations and secrets. Then write the Docker file, apply optimization tactics like multi-stage builds, and finally verify the container locally before pushing it to a registry. If you skip local validation using the Docker run command, you will deploy broken artifacts that crash immediately in production and trigger costly rollback procedures across your infrastructure team. A common pitfall in migration is the fat container. You should follow the one process per container philosophy. If your application has multiple components, use orchestration tools like Kubernetes to manage them as separate services rather than bundling everything into a single image. Combining web servers and background workers into one process will monopolize CPU resources and prevent independent scaling, which directly violates cloud-native design principles tested on certification exams. Let's check your understanding. If a legacy application writes logs to a local file on the disk, what happens to those logs when the container restarts? The correct answer is that they are lost because containers are ephemeral. You must configure the app to write logs to standard output so orchestration platforms can aggregate them. Failing to redirect output will cause you to miss critical audit trails and violate compliance requirements for centralized logging in regulated environments. We covered the core concepts of containerizing applications for migration. Containerization eliminates environment parity issues by bundling the runtime with the code. It provides portability across cloud providers and requires a stateless design. Security is maintained by running non-root users, and orchestration handles scaling and networking. If you ignore these principles, your deployment will suffer from configuration drift and security vulnerabilities that fail automated compliance checks during production release cycles. For the AZ-305 exam, focus on Dockerfile syntax and best practices. You will likely encounter questions about ephemeral storage risks and the need for external databases. Pay attention to non-root user configurations and multi-stage builds for optimization. Remember that containers should be lightweight and stateless. Misinterpreting volume mounts as persistent storage will cause you to select incorrect answers during scenario-based questions regarding data durability and long-term disaster recovery planning. Imagine you're planning a move to a new office building. You budget for the movers and lease up front, but signing a contract for a massive warehouse when you only need a small suite will crush your monthly overhead. Migration cost planning prevents that sticker shock by aligning cloud spend with actual business needs. On the exam, calculate egress fees from Azure Blob Storage and factor in vCPU ratios for VM scale sets. Skip this step, and unmonitored data transfers will drain your operational budget. In this lesson, we will cover the 3 buckets of migration costs: master the right sizing strategy, explore storage tiering options, review commitment models, and map out the optimization lifecycle. You will learn to run as monitor metrics list with specific namespace filters to catch waste early. If you skip these steps, your architecture will suffer from idle resources that silently inflate your monthly bill and delay critical deployment timelines. Migration cost planning is the disciplined process of forecasting, budgeting, and controlling financial impacts during workload transitions to ensure your target environment is architected for efficiency from day one. You must configure Azure Advisor recommendations with exact thresholds to track spend accurately. Failing to establish these controls will cause untracked resource sprawl that violates compliance audits and destroys your profit margins before launch. First, we look at one-time migration costs like planning, training, and data egress fees. Next, recurring operational costs cover compute, storage, and networking. Finally, hidden costs often catch teams off guard, including refactoring efforts and security compliance overhead. You must account for Azure Data Box shipments and manual rewrites for legacy applications. Ignoring these categories will cause sudden budget overruns that halt your production releases and trigger executive escalations. First, analyze legacy performance metrics to establish a baseline. Never trust source hardware specifications alone. Real-world utilization tells the true story. You should deploy Azure Monitor workbooks to capture actual CPU and memory percentages across your virtual machines. Relying on vendor specs instead of live telemetry will result in oversized instances that waste monthly spend and degrade overall system responsiveness. We specify the namespace and metric name to target CPU usage. The dimensions filter for a specific instance ID. We set start and end times over 7 days, use a daily period, and request the average statistic to smooth out spikes. Run the As-Monitor metrics list command with exact query parameters to extract this data. Missing these filters will return aggregated cloud-wide averages that mislead your scaling decisions and trigger unnecessary provisioning costs. First, analyze legacy performance metrics to establish a baseline. Next, right-size based on utilization percentiles to eliminate idle capacity. Target the P95 threshold for your compute workloads to guarantee steady performance during peak traffic windows. Choosing lower percentiles instead will cause sudden latency spikes that frustrate end users and violate your service level agreements. This JSON config defines the hardware profile with a specific VM size. The storage profile assigns an OS disk using premium LRE storage, ensuring performance matches the workload requirements without over-provisioning. You will apply this template through the as-vm create command with explicit SKU parameters. Skipping these precise configurations will default to expensive standard tiers that degrade application throughput and waste your monthly compute budget. First, analyze legacy performance metrics to establish a baseline. Next, right-size based on utilization percentiles to eliminate idle capacity. Finally, verify against business SLAs to ensure reliability. You must cross-reference your chosen VM families with Azure Service Level Agreements to validate uptime guarantees. Ignoring these contractual thresholds will result in architecture failures that breach compliance requirements and trigger automatic penalty clauses. We set the VM size to match our right-sized analysis. The tags block enforces governance by assigning a cost center and environment, ensuring every resource is trackable for optimization. You will enforce these controls using bicep scripts with mandatory metadata fields for every deployment. Failing to implement this structured tagging strategy will create unbillable sprawl that obscures your actual spend and breaks audit trails. Once you have a stable baseline, move from on-demand pricing to commitment models. Reserved instances offer deep discounts for steady-state workloads over 1 to 3 years. Savings plans provide flexibility across families while still delivering significant savings. You should evaluate your predicted monthly compute hours against Azure hybrid benefit rules before committing funds. Choosing the wrong model will lock you into rigid terms that waste budget when traffic patterns shift unexpectedly. Hot storage suits frequent access with higher costs. Cool or infrequent tiers optimize for monthly access at lower rates. Archive storage targets rare access and long-term retention for the lowest possible cost. You must configure lifecycle management policies in Azure Storage to automatically transition blobs after 30 days of inactivity. Misplacing critical files in cold tiers will cause severe retrieval delays that break application workflows and increase operational friction. The lifecycle begins by monitoring resource usage. You analyze the data to identify waste, optimize configurations based on findings, and automate recurring tasks to sustain efficiency over time. You will implement Azure Auto-Scale rules with defined scaling thresholds to handle predictable load changes automatically. Skipping this automation step will force manual interventions that delay deployments and introduce human error into your production environment. Adopt a FinOps mindset where cost becomes a first-class metric alongside latency and uptime, empowering developers to see the financial impact of their infrastructure decisions in real time. You must integrate cost alerts directly into your developer dashboards using Azure Cost Management, APIs. Ignoring this cultural shift will cause engineering teams to prioritize speed over sustainability and generate unpredictable monthly invoices that derail project roadmaps. When right-sizing, which metric should you prioritize to avoid overprovisioning? The answer is average or P95 utilization, as peak theoretical capacity often leads to wasted budget in the cloud. You must verify your selected instance families against actual workload requirements before approving any changes. Choosing higher tiers based on guesswork will lock you into expensive monthly commitments that drain your operational reserves and slow down delivery cycles. For the exam, focus on cost optimization scenarios and look closely for egress fee traps. Remember that tagging is mandatory for effective tracking, and always recommend right-sizing based on telemetry rather than legacy specs. You should prioritize Azure Advisor recommendations that explicitly address underutilized resources and unattached managed disks. Overlooking these specific exam patterns will cause you to miss critical scoring points and misunderstand the core financial architecture principles. Visibility is the foundation of cost management. Right-size your workloads instead of copying legacy specs. Treat optimization as a continuous loop, automate recurring tasks, and leverage commitment models to secure long-term savings. You must implement automated budget alerts with specific spending thresholds to catch anomalies before they escalate. Ignoring these final steps will result in uncontrolled expenditure that undermines your entire cloud strategy and damages stakeholder confidence. Imagine you need to move a library of 10,000 heavy books to a new city. You could mail them one by one, but that would take years and risk losing pages along the way. Instead, you rent a moving truck, load it securely, and drive it over. Offline migration works exactly like this truck for petabytes of data. When your dataset outgrows your network pipe, shipping Azure Data Box hardware directly to the provider bypasses bandwidth throttling entirely, preventing costly project delays that derail cloud adoption timeline. We will cover the mathematical reasoning behind choosing offline migration, compare it directly against ExpressRoute and online replication methods, walk through the complete data box lifecycle step by step, and examine the exact PowerShell commands you use to copy and verify your data safely. Mastering these steps prevents misconfigured storage accounts and ensures your petabyte-scale workloads transition smoothly without breaching compliance or missing critical deployment deadlines. Let's examine the actual metrics that drive your migration strategy. Time to transfer, commonly abbreviated as TTT, serves as your primary decision threshold. Moving 100 terabytes across a single gigabit link requires approximately 12 days under ideal conditions. Real-world network congestion and packet loss consistently extend those timelines beyond acceptable maintenance windows, forcing you to switch to physical appliances before budget overruns or failed sync attempts derail your entire infrastructure modernization effort. Before you submit any hardware request, you must evaluate the fundamental trade-offs between online replication and offline transport. Online methods leverage ExpressRoute or standard WAN links and perform exceptionally well for terabyte-scale repositories, but they quickly become cost-prohibitive and time-consuming at petabyte scales. Physical appliances eliminate network dependency entirely, delivering sustained multi-gigabit write speeds while introducing initial provisioning complexity that requires careful capacity planning to avoid storage allocation failures. Here is the complete architectural flow for this process. Your source data initially resides in on-premises NAS or SAN arrays. You direct your copy commands toward the ruggedized appliance, which temporarily registers as a local endpoint extending your Azure Blob storage namespace. Once the drive reaches capacity, you dispatch it to the regional data center, where engineers securely onboard the volume directly into your target container, eliminating network bottlenecks that routinely cause partial sync failures. Let me break down the exact sequence you must follow during deployment. We will track this procedure cumulatively, so pay close attention to how each phase logically builds upon the previous configuration step. Skipping verification protocols or misordering the provisioning workflow frequently triggers authentication failures and leaves your storage accounts in an inconsistent state that requires manual intervention before you can safely proceed with bulk data ingestion. Once the appliance connects to your local network, you must execute the actual data transfer sequence. Robocopy remains the industry standard for Windows-based workloads in this scenario. You will deploy the multi-thread parameter to push 64 concurrent streams across the link. Configure retry logic to handle transient errors 3 times with a 2-second interval. And enable comprehensive logging to maintain an immutable audit trail that satisfies compliance requirements during certification reviews. Now that we have established the ordering and initial copy procedures, let us integrate the critical verification phase. You must guarantee absolute data integrity before dispatching the hardware back to the provider. This requires systematically generating SHA-256 checksums across every source file to mathematically prove nothing was corrupted during transit, preventing irreversible data loss that would force you to restart the entire multi-week provisioning cycle from scratch. To verify integrity during this phase, we utilize PowerShell to generate SHA-256 hashes for every single file within your source directory. The getChildItemCMDlet recursively traverses the entire folder structure, computes cryptographic identifiers for each item, and exports the complete dataset to a structured CSV file. You will cross-reference these local values against the cloud platform outputs after ingestion completes, catching silent bit rot that would otherwise corrupt your production workloads without triggering any alerts. Finally, we arrive at the shipping and incremental synchronization phase. Once verification passes, you trigger the dispatch status directly in the Azure portal to generate your secure shipping label. While the physical drive travels through the logistics network, your local repositories will inevitably accumulate new writes. You must architect a final delta sync strategy using scheduled replication jobs after the bulk upload completes, preventing data drift that would cause critical application failures upon cutover. To be precise, offline migration represents the standardized practice of transferring massive data volumes using physical storage appliances rather than relying on public internet protocols. This architectural approach completely bypasses bandwidth throttling and latency constraints by physically routing hardware directly to the cloud provider regional data center. Implementing this method correctly prevents severe throughput bottlenecks that routinely stall enterprise modernization efforts, while misconfiguring the endpoint permissions can trigger immediate access denials during the initial provisioning phase. Remember this core principle without exception. Data integrity remains absolutely paramount throughout the entire migration lifecycle. A rapid copy operation that silently corrupts your underlying files will inevitably cause catastrophic application failures downstream. You must rigorously verify cryptographic hashes before dispatching the hardware, because once the drive leaves your secure facility, retrieving and reprocessing corrupted blocks becomes prohibitively expensive and forces you to completely restart the provisioning workflow under strict compliance audits. Let us quickly check your practical understanding of this workflow. Suppose you are transferring 50 terabytes of structured data to a data box appliance using Robocopy. Which specific multi-threading parameter would you invoke to maximize throughput across concurrent streams? And what exact retry interval should you configure to efficiently handle transient network errors without overwhelming the local storage array or triggering unnecessary timeout exceptions during certification testing? Watch carefully for several common implementation pitfalls that frequently trap candidates during certification exams. First, absolute file count consistently outweighs raw storage size in performance calculations. 1 terabyte containing 1 million tiny documents requires significantly more IOPS and metadata processing than a single large archive due to file system overhead. You must bundle small files into compressed archives before copying, while also reserving a 20% capacity buffer to accommodate retry logic and prevent premature drive allocation failures. We have thoroughly covered both the strategic rationale and technical execution of offline migration workflows. You now understand that petabyte-scale repositories absolutely require physical transport to completely bypass traditional bandwidth limitations. We systematically walked through the complete data box lifecycle, progressing from initial provisioning and local connectivity to executing Robocopy transfers and verifying cryptographic hashes. We also highlighted critical pitfalls like excessive file counts and explained why implementing delta synchronization prevents catastrophic data drift during final cutover phases. For the certification exam, you must prioritize mastering the specific decision criteria that differentiate migration strategies. Know exactly when to select offline transport versus online replication based strictly on dataset volume and available bandwidth thresholds. Remember that data box functions as a temporary storage extension directly integrated within your management portal. You will also encounter scenario-based questions testing Robocopy parameter selection and demanding explicit justification for verifying checksums to guarantee absolute data integrity before production cutover. Imagine you're designing a highway system where traffic volume doubles every month. If you only build wider roads, you will eventually run out of space and budget. Cloud performance works the same way. It is not just about raw speed, but about intelligently matching your infrastructure to demand so it scales seamlessly without breaking the bank. On the AZ-305 exam, you must configure Azure Autoscale with precise metric thresholds like CPU exceeding 60%, because failing to right-size resources leads to costly overprovisioning. We will cover how to select the right resources, review architectures regularly, monitor performance continuously, and make informed trade-offs. By the end, you will know exactly how to architect for speed and efficiency on Azure. You will learn to run as-VM scale-set commands correctly, because misconfigured instance counts cause deployment failures and violate performance SLAs during peak traffic windows. First, we look at selection. You must match compute and storage to your specific workload requirements rather than using a generic approach. Next is review. Technology evolves fast, so you should regularly update older services for better efficiency. Then comes monitoring, because you cannot optimize what you do not measure. Finally, consider trade-offs, understanding that strong consistency increases latency while eventual consistency improves speed. Exam questions test when to apply Azure SQL Managed Instance versus Cosmos DB, because choosing the wrong model causes slow response times under load. In the Azure well-architected framework, performance efficiency is defined as the ability to use computing resources efficiently to meet system requirements. It ensures your architecture remains agile and cost-effective as demand changes and new technologies emerge. You must document baseline metrics like 30 milliseconds for IPI calls, because ignoring these targets leads to unoptimized resource allocation and unexpected billing spikes during production workloads. When selecting infrastructure, you need to know your options. Virtual machines offer full control but require manual scaling. Azure Functions provides serverless compute that scales automatically based on events. For storage, blob storage handles massive unstructured data efficiently, while premium SSDs deliver the low latency required for high-throughput databases. You must configure AZ VMSS scale parameters correctly, because mismatched instance sizes cause deployment failures and violate performance SLAs during peak traffic windows. One of the most effective ways to improve performance is implementing caching. This Python snippet shows how you would interact with an Azure Redis cache instance. First, it checks the cache for a user profile. If found, it returns the data immediately. On a miss, it queries the database and stores the result in the cache with a 1-hour expiration to keep data fresh. Setting default expiration in seconds to 3,000 prevents stale reads, while reducing primary database load by 80% during concurrent access. Visualizing the data flow helps you spot bottlenecks. In a well-architected system, static assets are served directly from a CDN edge location. Dynamic requests hit an application service, which checks a Redis cache before querying the primary SQL database. This layered approach drastically reduces latency for global users. Configuring AZ CDN endpoint rules correctly prevents origin server overload and ensures sub-500 millisecond response times for international traffic patterns. We will walk through implementing a high-performance architecture step by step. First, we design for scale by configuring auto-scaling rules that match infrastructure size to real-time demand. You must define cooldown periods of at least 120 seconds, because rapid scaling triggers cause resource contention and violate stability SLAs during sudden traffic spikes. This JSON configures an auto-scaling rule for your virtual machine scale set. It defines a profile with a minimum of 2 and maximum of 10 instances. The metric trigger watches CPU usage, scaling out by 1 instance whenever load exceeds 70%. Setting cooldown to 300 seconds prevents thrashing and ensures predictable compute costs during sustained high-load scenarios. Next, we implement caching and content delivery networks. By placing frequently accessed data in memory and serving static assets at the edge, you drastically reduce round-trip latency for end users. Configuring AZ Redis replication factors correctly prevents single points of failure and maintains consistent throughput when primary nodes experience network partitioning. This Python script connects to an Azure Redis cache instance. It first checks for a cached user profile using the ID as a key. If data exists, it returns it immediately. Otherwise, it queries the database and stores the result with a 1-hour expiration to prevent stale reads. Setting max memory policy to all keys LRU evicts least recently used entries automatically, preventing out-of-memory errors during sustained write operations. Finally, we monitor and iterate continuously. You must track performance metrics regularly to identify bottlenecks early and adjust your architecture as business requirements evolve. Configuring as-monitor log analytics queries correctly ensures you capture critical latency spikes before they cascade into full service degradation during peak operational hours across global regions. This KQL query tracks application performance over the last hour. It groups requests by 5-minute intervals and calculates the average duration per endpoint. The results are sorted by slowest response time, helping you spot bottlenecks quickly. Adding where duration greater than 200 filters out normal traffic patterns and highlights actual latency violations requiring immediate architectural intervention. Remember that performance is continuous. It requires ongoing monitoring and iteration rather than a one-time setup. Always let telemetry data guide your architectural decisions instead of relying on intuition. Ignoring Azure Application Insights alerts leads to undetected memory leaks and causes catastrophic service outages when concurrent user sessions exceed configured capacity limits. Let's check your understanding. Which consistency model typically improves data accuracy but may increase latency? Think about how strong consistency forces immediate replication across replicas, while eventual consistency prioritizes availability and lower latency. Choosing the correct Cosmos DB consistency level prevents data inconsistency errors during distributed transactions while maintaining acceptable response times for read-heavy workloads. We covered matching infrastructure to workload requirements, implementing caching to reduce database load, using serverless and CDNs for global scale, and monitoring metrics to guide optimization. These principles will help you build resilient and cost-efficient architectures. Applying as-ax create with optimized node pools ensures predictable scaling behavior while preventing resource exhaustion during sudden production traffic spikes. For the AZ-305 exam, focus on knowing when to use Redis versus CDN for specific scenarios. Identify performance bottlenecks in case studies, configure auto-scaling rules correctly, and evaluate trade-offs for consistency under load. Practice reading architectural diagrams to spot inefficiencies quickly. Misconfigured as-monitor alert rules cause false positives that waste engineering hours during critical production incidents. Imagine you are driving a long road trip with the heater on full blast and windows cracked open. That is exactly what running cloud infrastructure without cost controls feels like, because you are burning through budget for zero actual progress. Today, we will explore how to stop that waste and turn your cloud spend into a strategic asset. We will cover the cost optimization pillar principles, walk through right-sizing virtual machines using Azure Advisor recommendations, and implement automated spending limits with cost management budgets, so you never face unexpected billing shocks during production deployments. By the end of this lesson, you will understand 4 key areas: foundational cloud financial management principles, matching resources to actual workload demands, storage lifecycle automation for data efficiency, and implementing cost controls in your environment. We will also review common pitfalls that trip up architects during certification exams. You must master these concepts because failing to align compute capacity with actual throughput directly triggers over-provisioning charges, and missing tagging standards completely breaks your ability to allocate budgets accurately across engineering teams. Cost optimization is not about finding the cheapest provider or stripping away necessary features. It focuses on maximizing business value while eliminating waste. The framework guides you to adopt a consumption model where you pay strictly for what you use, measure efficiency against business metrics rather than raw bills, and leverage managed services to stop managing undifferentiated heavy lifting. When applied consistently, organizations typically see up to 35% reduction in unnecessary cloud expenditure within the first year. Missing this balance often leads to performance degradation when teams cut costs without validating workload requirements. Cloud financial management, commonly known as FinOps, is a cultural practice that brings engineering teams together with finance and business stakeholders to make informed data-driven decisions about cloud spending. It establishes clear accountability through tagging strategies, shifts the focus from static infrastructure ownership to dynamic consumption tracking, and ensures that every architectural choice aligns with measurable business outcomes rather than isolated technical preferences. Failing to implement this discipline often results in shadow IT sprawl and unallocated spend that completely bypasses your central billing alerts. This bicep configuration demonstrates how to right-size your compute layer and enforce a consumption model automatically. We define the virtual machine scale set with an instance type matching memory requirements. Next, we set the initial capacity to 2 instances and disable overprovisioning to avoid paying for idle resources. When usage crosses the 70% threshold, the system automatically increases the instance count by 25%, ensuring you only pay for exact capacity during traffic spikes. Skipping these parameters typically results in paying premium block blob rates for historical logs that migrate to archive tiers. Understanding storage tiers is essential for eliminating waste. High-performance options are necessary for active workloads, but retaining them for dormant data quickly inflates your monthly bill. You must match the access frequency of your datasets to the appropriate pricing tier. This table outlines the standard cloud storage categories, their typical use cases, and how their cost structures shift as data moves through its lifecycle. Failing to implement proper lifecycle rules results in paying premium blob storage rates for infrequently accessed logs that should reside in archive tiers. Effective cost optimization follows a continuous feedback loop rather than a one-time configuration step. You must first monitor actual usage metrics to establish a baseline performance profile. Next, you analyze underlying cost drivers to identify overprovisioned or idle resources. Then you apply right-sizing rules and scaling policies to match capacity with demand. Finally, you implement lifecycle automation to retire stale data and enforce tagging standards. Skipping this iterative process typically causes resource drift, where unused compute instances continue generating recurring monthly charges without alerting your finance team. We are now walking through the first phase of implementing cost controls. You will begin by establishing strict tagging and accountability protocols across every resource group. Configure mandatory metadata fields like cost center and owner directly in your deployment scripts to enforce governance from the initial provisioning stage. Failing to lock these metadata fields early typically leads to unallocated spend that completely bypasses departmental budgets and complicates later financial audits during certification scenarios. This configuration shows how to automate storage lifecycle policies directly within your container definitions. We enable the lifecycle management rule and apply a prefix filter to target specific log directories. Next, we instruct the system to move matching blobs to cooler storage after 15 days of inactivity. Finally, we set a 30-day deletion window to automatically purge outdated data, ensuring you never pay for high-performance storage when archival tiers would suffice. Skipping these transitions typically results in paying premium block blob rates for historical logs that migrate to archive tiers. Moving into the second phase, we integrate auto-scaling and right-sizing mechanisms directly into your deployment pipelines. This ensures that compute capacity breathes in sync with actual application demand rather than relying on static, oversized allocations. You will configure virtual machine scale, set profiles within your ARM templates to dynamically adjust node counts based on real-time memory pressure. Failing to bind scaling triggers to specific metrics typically causes performance bottlenecks during traffic surges or unnecessary compute charges during off-peak hours. This CLI workflow demonstrates how to enforce tagging hygiene and automate scaling limits in a single operational flow. We first set the active subscription context to ensure commands target the correct budget envelope. Next, we apply a mandatory environment tag to the resource group and lock it to prevent unauthorized modifications. Then, we provision an auto-scale profile that binds directly to the web app, establishing minimum and maximum instance bounds. Skipping these steps typically results in orphaned resources, accumulating unexpected monthly fees or uncontrolled scaling events. We are now entering the final phase of implementing cost controls. You will layer lifecycle automation and continuous monitoring directly on top of the existing governance framework. This closes the feedback loop by automatically retiring idle resources and tracking efficiency metrics against specific business goals. Implement Azure Monitor alerts paired with automated runbooks that terminate unattached managed disks after 30 days of low activity. Failing to close this loop typically allows zombie resources to silently accumulate recurring storage costs that inflate your total cost of ownership beyond acceptable thresholds. Optimization is not a one-time configuration. It is a continuous cycle of measuring, adjusting, and aligning infrastructure, spend with evolving business value. You must establish recurring cost review meetings that examine Azure cost management reports and validate resource utilization. Ignoring this ongoing process typically results in architectural drift, where legacy workloads consume disproportionate compute quotas, while newer applications starve for processing power during peak windows. Let us check your understanding of the core pillar we just covered. Which well-architected framework component specifically focuses on eliminating unneeded resources and ensuring you pay only for what you actually consume? You must recognize that this component directly impacts certification scoring by testing whether you can identify right-sizing opportunities, implement auto-scaling rules, and enforce strict tagging policies across environments. Misidentifying this pillar often leads to selecting expensive managed databases when simpler PaaS alternatives would satisfy the workload requirements. We have covered the essential pillars of cloud financial management and practical deployment strategies. You now understand how to prioritize business value over raw price tags, implement automated scaling and lifecycle policies, enforce strict visibility through tagging, and design architectures that align with efficiency goals. These practices form the foundation of a sustainable cloud environment. Failing to integrate these controls typically results in unmanaged resource sprawl, where orphaned virtual networks and unused managed disks silently accumulate monthly fees that breach your approved budget thresholds. For the AZ-305 exam, focus heavily on recognizing when to recommend managed services versus self-hosted alternatives to reduce total cost of ownership. Pay close attention to questions involving data egress fees and cross-region transfer costs. Practice identifying right-sizing mismatches in workload scenarios and master tagging policies that enable granular cost allocation across departments. Misinterpreting these objectives typically leads to selecting expensive virtual machine scale sets when serverless functions would perfectly handle variable traffic patterns while reducing monthly compute bills. Imagine you're renovating a busy highway interchange while traffic is still flowing at full speed. You cannot simply shut down the roads. You must carefully build new lanes, divert vehicle streams without causing gridlock, and only close the old pavement once the new system handles the load. That mirrors enterprise cloud migration perfectly. In this lesson, we will walk through Global Logistics Corp as they design a resilient strategy using Azure landing zones, balancing legacy constraints with modern architecture while avoiding costly downtime. Here is exactly what we will cover today. We start by exploring the strangler fig pattern as your blueprint for incremental migration. Next, we establish secure network connectivity using Azure ExpressRoute and handle database replication without breaking the chain. Then, we dive into infrastructure as code to guarantee repeatability across environments. Finally, we discuss security architecture and common pitfalls like unexpected egress costs that can derail your monthly budget if you do not monitor data transfer volumes carefully. Let us define the core strategy we are using, the strangler fig pattern. This approach avoids a risky Big Bang migration by gradually replacing specific functionalities of your legacy system with modern cloud services. You build an IPI gateway facade around the old monolith, route traffic to new microservices piece by piece, and eventually decommission the old system once it is completely strangulated. It prevents deployment failures that could halt business operations during peak hours. Now let us get to work on designing this migration using a cumulative approach. First, we must establish the foundation before moving any workload. You need to bridge the gap between on-premises and cloud by implementing Azure Site-to-Site VPN with 256-bit IES encryption to ensure secure communication during the transition. This step prevents unauthorized data leakage and guarantees that your legacy applications can reliably communicate with new cloud endpoints throughout the entire migration window. Visualizing this first step is crucial for your exam preparation. The diagram shows how data flows during the connectivity phase. You start with the legacy on-premises database, then route traffic through a secure site-to-site VPN tunnel directly into your cloud VPC. From there, the traffic hits the new cloud services. This visual confirms that all data paths are encrypted and routed through controlled gateways before reaching the public internet, preventing exposure to untrusted networks. Next, we move to the core execution phase. Once connectivity is live, you begin refactoring and migrating data using Azure Database Migration Service with continuous replication enabled. You transition logic to containerized services while actively strangling the monolith by swapping out pieces of functionality. If you skip validation checks here, you risk data corruption or service downtime that could disrupt customer transactions across multiple regions simultaneously. Let us look at how we implement this refactoring using infrastructure as code with Terraform. This configuration defines the target environment for our microservices by creating a VPC with a 16 CIDR block to isolate production traffic. We then define an IKS cluster, linking it to private subnets and assigning a managed identity role. This code ensures that our containerized services have a secure, reproducible foundation ready to receive migrated traffic without manual configuration drift. Finally, we reach the decommissioning phase where you close the loop. Once all traffic has been successfully shifted to the new microservices and validation passes, you remove the legacy components. You decommission the old servers, revoke access keys via Azure ID, and clean up temporary resources. This step ensures you are no longer paying for dual environments and that security risks from unpatched monoliths are completely eliminated before your next audit. To support this final phase, you need strict governance using Azure Policy. This configuration block demonstrates how to enforce compliance during decommissioning by explicitly denying any action on resources tagged as legacy unless authorized by a specific migration role. This prevents accidental deletion of active services while ensuring that old, unused assets are systematically purged from your environment before they become security liabilities or cost drains. As you design this architecture, watch out for common traps that appear frequently on certification exams. Underestimating egress costs can blow your budget, so keep data locality in mind by placing high-chatty dependencies in the same region. Ignoring identity management is another risk. Always use managed identities instead of long-lived access keys. Finally, avoid the lift-hand shift trap by choosing PaaS offerings over DIY/VMs to reduce operational overhead and maintenance burdens. Security must be integrated into this design from day one, not bolted on later. You are responsible for securing data, identity, and application logic within the cloud environment. Implement encryption in transit using TLS 1.2 or higher, and ensure data at rest is protected with Azure Key Vault managed keys. Adopt a zero-trust model by authenticating every service-to-service call through a private endpoint. This shared responsibility model ensures you secure the workloads while the provider secures the underlying infrastructure. Keep this principle in mind as you design your architecture for production workloads. Migration is not just a technical upgrade. It is a fundamental shift in how you manage risk and monthly cloud spend. The cloud provider secures the infrastructure, but you own the security of your data and applications. Embrace this shared responsibility to build a resilient system that scales efficiently without compromising safety or triggering unexpected compliance violations during audits. Let us check your understanding before we move forward. In the strangler fig pattern, why do we recommend using infrastructure as code during the refactoring phase? Is it primarily to reduce storage costs, to ensure repeatability and version control, or to automatically scale the database? Review how code-based definitions help you manage complex migrations and prevent configuration drift when applying updates across multiple environments simultaneously. We have covered the essentials of enterprise migration design for your certification exam. You learn to use the strangler fig pattern for incremental, low-risk migration while establishing secure network connectivity as the foundation. We emphasized refactoring with ISC tools like Terraform and highlighted security as a shared responsibility model. Remember to monitor cloud, spend continuously using cost management, and leverage managed services to reduce operational overhead before deploying to production. For the AZ-305 exam, focus on these key areas that frequently appear in scenario-based questions. You will likely be asked to choose the right migration pattern based on downtime requirements. Remember that strangler fig minimizes risk for complex monoliths. Review how to design landing zones with Azure Landing Zones for governance and understand when to use managed databases over VMs. Finally, be prepared to calculate cost implications of data transfer and storage options accurately. Imagine a bank vault that holds your most sensitive cash, but you also need ATMs scattered across the city so customers can access funds instantly. That is exactly what hybrid infrastructure feels like for modern enterprises, keeping critical assets secure in a private data center while extending reach and scalability via the public cloud. In this lesson, we will explore the ScaleMart scenario to understand why organizations choose hybrid architectures. We will examine connectivity options like Direct Connect, walk through infrastructure as code implementation using Terraform, and review critical security practices and exam pitfalls. ScaleMart is a retail giant facing a classic hybrid challenge. Their core database contains historical customer loyalty data that must remain on-premises due to strict regulatory compliance. However, their web storefront experiences massive traffic spikes during sales events that on-prem servers cannot handle alone. This scenario highlights why 90% of large enterprises adopt hybrid models. You need the security and sovereignty of private infrastructure alongside the elasticity of public cloud services. Let us trace the data flow for ScaleMart. A customer visits the storefront hosted in AWS. The web server processes the request and needs to validate inventory. Instead of hitting the public internet, traffic flows through a dedicated direct connect link directly into the on-premises data center. This private circuit ensures low latency and consistent bandwidth, bypassing the jitter and congestion of the public internet. To implement this hybrid stack, we follow a structured approach. First, we must identify data residency requirements to ensure compliance boundaries are clear before provisioning any resources. Here is how we define the providers in Terraform to manage both environments. We configure the AZ provider for the cloud region and the vSphere provider for the on-premises data center. This dual provider setup allows a single code base to orchestrate resources across the hybrid boundary, ensuring consistent state management. Next, we provision the private connectivity. This involves setting up the direct connect link and configuring the routing tables to ensure traffic flows efficiently between the cloud VPC and the on-premises network. This JSON configuration creates the direct connect link. We specify the location, bandwidth, and VLAN to match the on-premises router. The routes block defines which CIDR ranges should traverse this private connection, ensuring only authorized traffic uses the dedicated circuit. Finally, we unify identity and security. We extend the on-premises Active Directory to the cloud using managed services, ensuring a single source of truth for authentication and applying zero trust principles across the hybrid boundary. This IAM policy snippet demonstrates cross-account trust for the hybrid environment. It allows the on-premises identity source to assume a role in the cloud, but only when a specific external ID is provided. This adds an extra layer of security to prevent unauthorized access across the boundary. As you design hybrid solutions, watch out for common pitfalls. Hairpinning occurs when traffic routes back to the data center unnecessarily, creating latency bottlenecks. Egress costs can also spiral if you do not optimize data transfers between cloud and on-premises environments. Zero trust is a critical concept for hybrid architecture. It means treating every request as untrusted, regardless of whether it originates inside the office or from the cloud. You must authenticate and encrypt every interaction, ensuring that a breach in one segment does not compromise the entire network. Always perform a latency audit before deploying hybrid architecture. If your application logic requires hundreds of small database queries between the cloud and on-premises, your application will perform poorly regardless of how fast your connection is. Let us check your understanding. In a hybrid scenario, why is Direct Connect preferred over a standard internet VPN for database traffic? Think about performance and security implications. We covered the ScaleMart case study to illustrate hybrid infrastructure. You learned about connectivity with Direct Connect, implementation via Terraform providers, and the importance of unified identity. Remember to avoid hairpinning and manage egress costs carefully. For the AZ-305 exam, focus on designing secure hybrid solutions. You may be asked to choose between Direct Connect and VPN based on latency requirements, or to identify best practices for identity management. Always consider data residency and cost optimization in your answers.